Okay, good morning, everyone. Welcome back. Yesterday we saw the MIMO performance gains. The MIMO system will give you minimum of NT, NR. So if you have a NT transmit antenna, and if you have a NR receive antenna, so there is a performance degree of freedom gain is min NT, NR. Okay, so this is the degree of freedom gain or spatial multiplexing gain. So this plot shows the capacity versus SNR. I explained to you this curve is for the CISO case, single input, single output system. At 20 dB SNR, it is giving you 5. If you go here, and if you see, it will give you for the single input, single output system, give 5 bits per second per hertz. But the MIMO system with the 4 transmit antenna and 4 receive antenna is giving you 20 bits per second per hertz. So there are 4 time capacity improvement for given signal noise ratio. That 4 time is the min of NT, NR. Okay, so that's the capacity improvement. For in this case, single input and multiple output case, we are getting a capacity improvement that is due to the beamforming gain rather than the multiplexing gain. Okay, for the CISO single input and multiple output system, the degree of freedom gain is going to be only 1. So this side of the plot is showing again NT, NR is 8 antenna. So you can see there is a 8 time capacity improvement at 20 dB SNR. So if you go here, you will see 5 into 8, 40 bits per second per hertz. So the degree of freedom gain is minimum of NT, NR. So we saw this one, and we also show the slope of the high SNR slope. This is the region for high SNR. The high SNR slope also will give you the degree of freedom gain. Okay, so here is the high SNR slope is 4, and here is the high SNR slope is 8. And we also saw last class, end of the class, in the low SNR regime, the MIMO and the CMO will perform almost same here. So we don't need, if the system is operating at the low SNR regime, we don't need a MIMO system. We can use CMO system to get the performance enhancement. So we get NR-fold power gain in the case of CMO system. So we saw this slide as well, nature of the performance gain. At high SNR, degree of freedom limited, min NT, NR fold, degree of freedom gain for MIMO gain, and the MIMO is crucial. For the low SNR, NR fold power gain only need multiple receive antenna. Okay, at all SNR, min NT, NR fold gain due to combination of both effect, power gain and the degree of freedom gain. So then we look at this slide at the end of the class. So the capacity is the channel capacity is the one showing how much gain, capacity gain that we will get from the MIMO system. But how to realize that capacity is the one we are going to see today. How to realize that capacity. It's saying for the 4 transmitter and 4 receiver antenna, we can get 20 bits per second per hertz at 20 dB SNR. So how do we get that 20 bits per second? So that's the thing we are going to see today, which is the architecture that achieve that capacity for the fast fading channel. So again, we are going to consider fast fading channel and the slow fading channel, okay? So the fast fading channel, the architecture is called V-BLAS architecture, vertical Bell Laboratory layer space-time architecture. So you have a, data stream, independent data streams are coded using turbo code or LDPC code, and it is going to be transmitted through these channels. So these streams are add together, you receive the signal, your received signal is going to be summation of, k is equal to 1 to nt hk, something like that, okay? So you will get all the streams are add together. You receive all the streams are add together at the receiver. You need to decode each of the stream independently without the interference. So the receiver, all the streams are add together, interfere each other, and we need to decode each of these stream without the interference. So we can use the receiver architecture we can use maximum likelihood ML, maximum likelihood estimator, but this is the nonlinear estimator and very complex to implement. Then we can use linear receivers. This is nonlinear, linear receiver, zero forcing architecture, or MMSE architecture, minimum mean square architecture. These two are linear receiver, can perform, but it won't achieve the capacity, okay? It won't achieve, for example, if you have a 4 transmitter antenna and 4 receiver antenna at 20 dB SNR, it won't give you 20 bits per second per hertz that capacity is promised. So these, I will show you. So as I we can use a linear receiver. The linear receivers are zero forcing and MMSE receiver. They can decode the stream, independent stream, but they won't achieve the capacity, okay? But there is a nonlinear receiver called MMSE, successive interference cancellation, that will achieve the capacity. So that's what the story today at the beginning, okay? So the slide is saying can get the performance gain by sending independent coded stream at each of the transmit antenna and jointly ML decoding. Yes, we can able to get the capacity. So why it's surprising? Because the signals received add together, interfere each other. So to get the receiver, come up with a receiver that decode this interfered signal is is a demanding task. So question is how to get the degree of freedom gain even when the stream interfere with each other. Okay, so because all these streams will be interfere at the receiver, are we able to get the capacity? So that's the surprising results. Okay, so now I'm going to talk about zero forcing receiver. As I said, zero forcing receiver have a few names. People say interferent nulling, zero forcing receiver, and decorrelator. All are same thing. Okay. Okay. So zero forcing have a three name: decorrelator, zero forcing, and interferent nulling. So all are same thing for zero forcing. So let's focus on the transmit antenna 1. So let's focus on this signal. So only this signal we are going to estimate. So the receive signal can be written as H1X plus this is the rest of the interference plus noise. So I hope you understand that equation. So the H1 is the channel between, this is a vector channel. Okay, so let's say the H1 is, H1 here is a vector contain, this is H11, we call H21, HNR1. So this H1 is H11, H21, HNR into 1. So this is the H1, okay? So the receive signal can be written as that form, okay? So receive signal Y is equal to H1, this is the H1, and this is the X1, plus the remaining signal. Remaining signal, here, these are the remaining signal. So when you are decoding at the receiver, all add together like this, okay? But when you are decoding this signal, these guises are, all these rest of the guises are going to interfere. Yeah, so when you decode this signal, all of the signal will interfere. So all of the remaining signal, this stream up to this NR stream, they are denoted here. These are interference. These are interference. So we are going to estimate only X1, but these guys are interference and plus noise. So this is the same equation as before. So Y is equal to Hx plus noise is the one, our normal MIMO channel equation. Okay, so this is NR into 1, and this guy is NR into NT, and this guy is NT into 1 vector, and this guy is NR into 1. So this equation, we can write it as a summation of HK, XK, and K goes from 1 to NT plus noise. We can write it like this matrix equation like this. And then we can write, consider we are taking, estimating the first stream. So we can write H1, X1, and then summation HK, XK, K not equal to 1 because we put the K here already, plus W. So we can write this equation, this equation, this equation. We can write it like that. So that's what is written here. Okay. So now, so we wanted to estimate this guy as X1 and treat all these guys as interference. So simple strategy is to null out the interference from other antennas. So let's consider we have only 2 antennas, but it can extend it to more antennas as well. Okay, so this is the H1 channel. Okay, this is the H1 channel, H1, and this is H2. So consider only 2 transmit antenna, only 2 transmit antenna. So H1 is this guy, this vector, and this is the H2. Okay, consider only 2 antenna. So your receive signal is here. okay? Your receive signal is here. What you do is you project the receive signal orthogonal to H2, okay? You project the receive signal Y orthogonal to H2 and you get this signal, okay, this signal. And from this signal you estimate X1. Once you project that orthogonally, your interference is null, and then from this signal you estimate the X1. So this is called, this is the concept for zero forcing or interference nulling or decorrelator, okay? But you will lose some signal to noise ratio because this signal is bigger. When you project it, you have a smaller signal. From smaller, you will lose some energy in the zero forcing case, okay? So that will come in a minute, okay? So simple strategy is null out the interference from other antennas. So you project the receive signal orthogonal to H2. This is the interference orthogonal to that. Then your interference is gone. So you work from this signal and to estimate X1. So, this is the receive architecture for bank of decorrelator. So as I said, decorrelator, zero forcing, interference nulls are all same, okay? So you have a receive and a signal here. So this interference nulling, projecting this signal and then extracting this X1 can be done by this equation here. This is the zero forcing receiver. So this equation will do projection and also estimation as well. So, the receiver for the zero forcing receiver is going to be look like that. Your receive signal is here. All the transmitted stream are estimated by multiplying H into H Hermitian into H. Inverse into H Hermitian. This is the receive signal, okay? So the receive estimation, this is the NT into 1 is going to give by H Hermitian H inverse H Hermitian Y, okay? So again, you will see. So this is all the streams are estimated using projection, interference, cancellation, etc. Okay, so this is the concept of zero forcing. So for example, if you consider this matrix, this is the matrix, okay? It have a NT transmit antenna, NT into NR dimension matrix. So if you take the first row of that matrix, okay, first row of the matrix and multiply by the receive signal, then you will get the first stream, okay? So what I'm saying is, if you, from this matrix is NT into NR, you take the first row and multiply the receive signal and you will get the first stream of this guy. And if you take the second row of this matrix and multiply the receive signal, you will get the second stream. So if you take the last row of this matrix, multiply the receive signal, you will get the NT stream as well. So this is the kind of a zero forcing receiver, okay? Any question? Okay, so zero forcing receiver is just receive signal into this matrix, okay, and you will get all the stream, okay. As I said, zero forcing receiver is not going to achieve a capacity. So here, the bank of decorrelator or zero forcing performance, you can see this is the bits per second per hertz, and this is the SNR. This plot is for NT transmit antenna 8, receive antenna 8, and IID relay fading channel. You can see this is the capacity of the channel capacity. This is the channel capacity. You know, if you see here, 20 dB, we will get 40 bits per second that we saw before as well. Now 20 dB, if you go here, it will give you 40 bits per second per hertz. This is the observation we got from the last few slides ago, okay? So this is the channel capacity. But when you use the decorrelator or zero forcing receiver, what is the bits per second that you are getting is this guy, okay? It is this guy. So you can see there's a performance gap between decorrelator and the channel capacity. So there is a performance gap. But there's one thing that you can notice, this slope and this slope are same. This slope and this slope are same. So that means the decorrelator achieve the the degree of freedom gain, but the capacity is not achieved, okay? So that's one thing that you need to notice, that this high SNR slope are same. So you can see that's what is mentioned here. The decorrelator or the zero forcing achieve the full degree of freedom that min nt comma nr of the MIMO channel because same SNR slope. Okay, that's what I said. The decorrelator achieve the degree of freedom gain at high SNR because the same slope are same, but there is a gap in the capacity. Okay, so that's what it's saying. But there is a still substantial constant gap at high SNR. The moderate and the low SNR, the performance is no good. Okay, so the decorrelator, even though it's achieved high SNR slope, it is not achieve the capacity. So that's the story about the zero forcing. So let's see how do we the next half an hour or so, we are going to see how to close this gap, and bring the receive architecture that achieve the capacity. So that's the story. So this is interferent null versus match filtering. So we saw match filtering last time. So if you have a receive signal y h1, x1, and summation of hk, xk, k not equal to 1 plus w, then you can use a match filter that I explained to you last time. Match filter is what you do is you multiply the receive signal by h1 conjugate and divided by its magnitude. This is the match filter. So this is or maximum ratio combining. This kind of receiver also you can use as well. You receive signal is multiplied by h1 conjugate and divided by its magnitude. That's called match filter or MRC, maximum ratio combining. So we are now comparing interferent nulling, which is the zero forcing receiver, and the maximum ratio combining. So there's one more receiver here. Maximum likelihood, this is nonlinear receiver, zero forcing, and MRC, maximum ratio combining or match filter. So we are now comparing these two guys in this slide. So interferent nulling, remove all the interference at the expense of reducing the SNR. So I told you, when you project the signal, your SNR, you end up with dealing with a smaller receive signal, so your SNR is reduced, okay? So that's what we saw here. You say, when you project the signal, when you project this bigger signal orthogonally to the interferent, you end up with this smaller signal, so that reduce the SNR. That's why your performance is bad, okay? So that's what it's saying here. Interferent nulling, remove all the interferent at the expense of reducing the SNR. Match filter, project H1 into maximize the SNR, but SANR may be bad. So if you do maximum ratio combining or match filter, it will enhance maximize the SNR, but it is not going to maximize the SANR. Okay, so the match filter will maximize the SNR. Okay, maximize the SNR, but it's not going to maximize the SANR. The MMSE we will see next few slides. This is the techniques maximizing the SANR. Okay. So much filtering or maximum ratio combining project onto H1 to maximize the signal to noise ratio, but SANR may be bad. Okay, so here is the performance. So this plot is the y-axis. The y-axis is the capacity of the maximum ratio combining divided by the capacity of 8 transmit and 8 receive antenna. And also the capacity of the zero forcing divided by the capacity of 8 by 8. So there are two plots. The solid line is for the maximum ratio combining divided by the capacity of the 8 by 8 transmit antenna, 8 receive antenna case. And this guy, the dotted line is the capacity of the zero forcing divided by C 8 by 8. Okay? So if these guys has achieved capacity, this will be 1. Okay, this will be, that ratio will be 1. So that maximum is 1, okay, because it's a normalized capacity in the y-axis. So you can see, you know, the much filter performing very good at the low SNR regime. So low SNR regime, the much filter is perform, or maximum ratio combining perform better, almost achieve the capacity because the maximum capacity over the channel capacity is 1 mean, it almost achieves the capacity at low SNR. But when SNR is high, its performance is degrading. Why is it? Because the maximum ratio combining is maximizing the signal to noise ratio. At low SNR, these interference between the streams are very less, okay, because at the low SNR, the interference between the streams are very less, because the maximum ratio combining is not cancel the interference, and interference is low, but is performing better. But when the signal to noise ratio is become higher, so these streams signal interference will be strong, the maximum ratio combining is not going to handle the interference, and its performance is less. Okay, and similarly, the decorrelator or the zero forcing normally cancel interference, but the low SNR, it is there's no interference, but the receiver is built to cancel interference. So we are kind of applying a over conservative solution. So the performance is bad, but when the high SNR, the interference will be there between the stream, the zero forcing will cancel those interference and performance is better. Okay, so that's the message from this plot. So I'll repeat again. This is the maximum ratio combining. At low SNR, there's no interference between the stream or the less interference, and it will enhance the signal to noise ratio. Your performance is better, capacity performance is better. But when the SNR become high, the stream, these streams interfere each other, the maximum ratio combining is not built to cancel interference, so the performance is reducing. But the zero forcing at the low SNR, it will cancel interference, but there's no much interference, so we are kind of applying a over-conservative solution to the situation, so the performance is not good. But at high SNR, there's interference, so zero forcing will handle the interference very well, and performance is here. But here you can see the capacity. Ideally we should have one capacity. You can see there's a big gap here, okay, back gap here. So how to remove this gap is the one we are going to see. We like to have a receiver that can achieve the capacity all the time, low SNR and high SNR regime. So that's the objective. So I will tell you that MMSE SIG will achieve capacity for low SNR and high SNR. It's going to be go like this, always 1, okay? So optimum linear filter. So now we are going to look at the MMSE, minimum mean square error receiver. So this is the receive signal again, okay? So the receive signal can be written as this form, H1 into X1, and summation of the remaining interference plus W. Seek a linear filter that maximize the output SANR. So the MMSE is maximize the signal to interference plus noise ratio. Maximum ratio combining, maximize the SNR, but MMSE receiver is going to maximize the signal to interference plus noise ratio. So seek a linear filter that maximizes the output signal to interference plus ratio at all SNR. Offer the optimum compromise between nulling. So this MMSE offers the optimum compromise between nulling and much filtering. Okay, it whitening the interference first and then much filter. This is the linear MMSE filter. Okay. So, for example, let's say consider this is the kind of a interference subspace. The decorrelator is projecting the received signal orthogonally to interference subspace. The optimum filter is somewhere here, and the merge filter is doing somewhere here. Okay, so high SNR, the MMSE achieve the decorrelator. At low SNR, MMSE achieve the merge filter. Okay, we saw in one of the previous slide, high SNR, the decorrelator is performing better. At the low SNR, the merge filter is performing better. That we saw it. You know, here, remember this plot at low SNR, merge filter is performing better. At high SNR, the zero forcing performing better. The MMSE is going to achieve this performance at the low SNR and this performance at the high SNR. So that's what we are going to see. That's what is said here. The high SNR, MMSE achieve the decorrelator or the zero forcing. At the low SNR, MMSE achieve the merge filter. So here, that's what is shown here. So this is the same plot. As I said, this is the each of the capacity of the receiver divided by C channel capacity C88. So this is the plot for the merge filter or the maximum ratio combining, and this is the plot for the zero forcing or interference nulling, and this is the MMSE receiver. Okay, you can see MMSE receive almost achieve the approach the merge filter performance at the low SNR. At high SNR, it achieve the zero forcing performance. So because it is designed to maximize the signal to interference plus noise ratio. Okay, so that is the MMSE receiver. Okay, MMSE receiver. But still, you can see there is a gap here. At low SNR, it's almost achieved the capacity because the ratio is 1. Okay, MMSE receiver achieve capacity because this is a MMSE receiver rate divided by the channel capacity. So if achieve the capacity, means this ratio become 1. Okay, so low SNR is achieving the capacity, but when the high SNR comes, there is a gap between the capacity. So how do we close this gap is the one we are going to show next, which is called MMSE 6, successive interference cancellation. So, this plot, MMSE improved the performance of the decorrelator at the moderate and the low SNR, does not remove the gap in the performance in high SNR. So that's what I said. MMSE doing a good job at the low SNR, but at high SNR, there is a gap here. So that's what is saying. Does not remove the gap in the high SNR performance at high SNR. To remove the gap, we have to go to a non-linear receiver. So these receivers, these three receivers are linear receivers. The zero forcing, maximum ratio combining, MMSE, these are all are linear receiver. Linear receiver mean easy to implement, the complexity is less. But this guy is a nonlinear receiver. This guy is a nonlinear receiver. Of course, this guy also nonlinear receiver. It is complex to implement. Okay, so to remove the gap, we had to go to nonlinear receiver. Okay, so this is the MMSE with the SIG receiver. Okay, this is the MMSE with the SIG receiver. So what this is doing is you have the receive signal here. You have a receive signal here. The MMSE receiver equation is very similar to the zero forcing equation, and you will have some additional term here. Some additional term. No, not like that. This is the kind of a MMS receiver, okay? So you take the, this matrix, you take the first row and multiply the receive signal, you can decode the stream 1. You can decode the stream 1, okay? Then what you do is you estimate that stream, and from the receive signal, you subtract that interference. So you estimate one of the stream already. Normally, we estimate the strongest stream. The strongest stream from all of these mean which of the column of that H matrix have a strongest gain. Okay, you normally estimate the strongest stream. Let's, the strongest stream is estimated. And then why we need to estimate the strongest stream? Because strongest stream, when you estimate the strongest signal, other signal will be interfering. But the strongest signal, when you estimate the strongest signal, you will be estimating performance is better because it's a stronger signal. So anyway, so you first estimate the strongest stream, and then from the receive signal, you subtract that stream, okay? So that's what is called successive interference cancellation. You subtract the receive signal from the strongest stream, and then estimate the second strongest stream. You estimate the second strongest stream, and then subtract the second strongest stream from the receive signal, and then you go further, and estimate all of the stream. So this is called MMSE successive interference cancellation. So every time you estimate the stream, you multiply your receive signal with one of these row. Okay, when you multiply the first row with the receive signal, you will estimate the stream 1. Then you second row receive signal and multiply the receive signal with the second row, you will estimate the second stream, and etc. So if you do a successive interference cancellation, you will achieve the capacity. So that's what is shown here. You can see here, this is again the capacity versus the rate of all of these receivers. Okay, rate of all of these receiver divided by the capacity. You can see MMSE SIG achieve the capacity. You see, it's always 1, 1, 1, 1, 1. And this is the MMSE receiver, and this is the match filter or the maximum ratio combining, and this is the zero forcing or interference nulling or decorrelator. And you can see the MMSE SIG achieve the capacity. Okay, how do we? So there is a proof in one of the tutorial question. If you want, we can do that proof. This is the capacity of the MIMO channel. This is the capacity of the MIMO channel. This is the MMSE signal to noise ratio, and we can prove why MMSE SIG which achieve the capacity. There is a nice proof. This is equality. This is not an easy proof. It's a very nice proof in one of the tutorial question. We can do if you want nowadays, isn't it? We can do that question. So why is MMSE SIG is optimum? We can prove this one, that is achieve the capacity. Okay, MMSE is information lossless at each stage, and the successive interference cancellation architecture implement the chain rule of information. This is the chain rule of information. That's why it's optima. MMSE SIG is optimum. Any question? Huh? That's what we show here. This MMSE SIG is the best one. It's achieve the capacity. You see, this is the ratio of the MMSE SIG capacity divided by the channel capacity. So if it is 1, it's achieve the capacity. And MMSE is the second performance better, but here is the, as I said, it's a nonlinear receiver. We need to do successive interference cancellation. But if you want a linear receiver, then you go with the MMSE, and you know. Any question? Architecture for? Uh, I think the architecture is yeah, SIG is more complex. This is a kind of architecture. Yeah. Yeah. So I don't have that slide. Sure. Any other question? Yeah, yeah, of course. Yeah, I mean, uh, if we, I think that's, if you want a less complex and reasonable good performance, we'll go with MMSE, okay? But if you go with good performance and if you are ready to sacrifice complexity, we had to go with the MMS receiver. But in the 5G, we use machine MIMO and MRC. This guy, MRC is the one. Match filter is the very, very less complex receiver. You multiply the received signal with the channel coefficient, complex conjugate, and divide by magnitude. So this guy is the very, very less complex receiver compared to all of them, because here you need to invert a big matrix here. You need to invert the matrix here for zero forcing, and MMSC you need to invert the matrix. Okay, so here MRC here. You don't need to invert any matrix, just a multiplication. So the beauty of machine MIMO, if you do a maximum ratio combining, it will give you a reasonably good performance because of the large number of array. And at the receive for the uplink, the base station will do a maximum ratio combining. For the downlink, the base station will do a maximum ratio transmission, MRT. It will do MRT, maximum ratio transmission, which is a kind of a transmit beamforming, because base station assume channel knowledge, and it will do maximum ratio transmission. So these maximum ratio combining at the receiver, maximum ratio combining at the transmitter is the less complex to all of these things. That is what your machine MIMO is doing in the 5GNR. Any question? Yeah. Obviously, it's good. Yes. As a receiver, MMSC SIG is the optimum, is achieve capacity. Similarly, there is at the transmitter you can do a similar concept. It's called dirty paper coding. I don't know you heard about it. That is the pre-coding techniques, again a nonlinear pre-coding techniques. So it's as I said, maximum ratio combining at the receiver, maximum ratio transmitter at the transmitter is a very less complex. And similarly, maximum ratio MMSC with the SIG at the receiver performing optimum at the receiver. Similar to this, you can do one transmitter pre-coding. It is called dirty paper coding. That is you do at the transmitter to get the full capacity. Again, dirty paper coding is a very complex techniques as well. So people don't use MMSC, SIG, and dirty paper coding, etc. Because of the complexity. Sorry? In the 6G phones, yeah. Receivers, yeah. We have connectivity to satellite links. Yeah. In that case also the SIG might be very costly. Yeah, very costly. You have to go with MRC, MRT, yeah. So this is the theory, and we know how to realize the capacity, etc. But when you implement MRC and MRT, we know it is not performing to the capacity limit, but it's a trade-off between complexity and the performance. Okay, so we will be seeing the pre-coding in later on. Oh, yeah, yeah. So we have a zero forcing receiver, and we also have a zero forcing precoder as well. Okay. We have a MRC precoder receiver. We can do a MRT. This is a precoder at the transmitter. These are will do. Okay. So if I delete this guy, these are the receiver. These are the transmitter. You do zero forcing precoder, MRT, and you can also do MMSC precoder as well. And corresponding precoder is called dirty paper coding. Dirty paper coding. Okay, dirty paper. Okay, so now I'm going to talk about fast fading versus slow fading. Okay, so this is another important stuff. So whatever the VBLAST, vertical Bell Laboratory Layer Space Architecture that I started with today morning, it is assuming a fast fading channel between transmitter and receiver. We have a fast fading channel. We have enough diversities there because the channel is fast faded. Okay, but what happened if the channel is not fast faded? Okay, what happened if the channel is not fast faded? Then we cannot do a VBLAST architecture. We need another architecture called diagonal blast. Okay, so that's what I'm going to talk about now. Okay, so fast versus slow fading channel. So far we have focused on the fast fading scenario. So that means this channel is fast fading. So it have many channel realization is there. So that means your information, your data stream will go through independently faded channels because it's a fast fading channel. So you will get a diversity as well. So, but if this channel is very slow fading, we cannot do a VBLAST architecture. In that case, we need a different, okay? So that's what it's saying. So far we have focused on the fast fading scenario. Can VBLAST achieve the outage capacity of the slow fading channel? I said, yesterday, the fast fading channel, the information theoretic measure is the ergodic capacity or the mean capacity. But the slow fading channel, the information theoretic measure is the outage capacity or outage probability. The question is, can VBLAST achieve the outage capacity of the slow fading channel? The answer is no, it cannot achieve the transmit diversity. In the fast fading channel, the transmit diversity is not important since there is already a plenty of time diversity. Because in the fast fading channel, the channel is very changing dramatically. Your coherent time is very small. So your entire stream will go through different coherent time, and you will have a lot of time diversity. Okay, you already have plenty of time diversity. But in the slow fading channel, your channels are constant for long time. The coherent time is large. So you won't get plenty of time diversity. In that case, you need a transmit diversity. So the VBLAST is not going to give you a transmit diversity. In that case, you need a different architecture. So that is called diagonal blast. Okay, in slow fading channel, there's no time diversity, so coding across transmit antenna become important. So we are going to talk about coding across transmit antenna. Okay, so challenge is to combine the SIG. So we are going to do a coding across the transmit antenna, and also we need to combine with the successive interference cancellation, SIG. So that's what we are going to look at. It's called DBLAST architecture. So I will explain to you what is the DBLAST architecture next. So the DBLAST architecture, easy to explain with the two transmit antenna, let's see. Okay, so so what's the so this channel, slow fading channel mean this channel, let's say this channel H1, which is contain H11, H21, H11, H21, and then this channel H2 vector is H21, H22, H12. So your channel is H1 and H2. So this is your channel. Okay. So what is the what we are going to do in the D-blast, because these channel vectors H1 and H2 are going to be slow fading mean they are going to keep constant for longer period. So your coherent time is large. Okay. So it's going to stay longer period. So what we had to do is D-blast mean your stream is going through half of the stream go through first antenna, the half of the stream go through the second antenna. So that means half of the stream is going through the H1 and half of the stream is going through the H2 channel. So that's what is called diagonal blast, because your stream is going to, not all the stream is going to through the one antenna, half of the stream go through one antenna and half of the stream go through the other antenna. So what will happen is at first kind of a time slot, n time, let's say this is the n, okay? And so first n time, what happened is this guy will go, this guy will go. So go through the second antenna. So this is going to be this stream. So entire stream I divided by, this is the first stream, the superscript saying the first stream, and then A, B part, two part, A part and B part. This is the second stream, the superscript denoted second stream. This is A part and the B part. So at first n time slot, you will send the first stream, half of the first stream, and this guy is not going to send anything. So this first antenna is not going to send anything. So this guy is sending, the second antenna sending this stream, okay? The second n time, what happened is, this guy, this second stream will go through this antenna, so XB1, and then this first stream will go through this antenna, okay? So this is XA2, okay? So you will see the old stream, okay? So let me write it here, XA1, XB1, and this is like that. So your stream, the first stream will go through the first and second antenna. The second stream, the half of the first stream is going through the first antenna. So what I'm saying is your entire stream is going through, half of them is going to one antenna, half of them going to the second antenna. So that's why it is called D-blast, okay, diagonal blast, okay. So what happened is, similarly you will repeat, okay. This guy is, stream goes, the first part of this stream is going here, the second part will go here. Goes like that, it will continue, okay? So you see diagonal, okay, the streams are going diagonally. So what we are trying to do is, half of the stream goes through H1, half of the stream goes through H2. So we are getting a diversity. We wanted to send the old stream through different channel, mean we will get a diversity. So that is the objective of D-blast. So you first receive from the this stream, okay, so you first receive, at the receiver, for the first n time slot, you will receive this guy. There's no interference because first antenna is not transmitting. You can easily receive this one, okay? You can easily receive that. Then what happened is, you receive second stream, second n time slot, you will have both antenna is transmitting, but you estimate this one, you estimate this guy, okay, you estimate this guy, and then subtract from this portion and you estimate this one. So you You receive this one without problem because there's no interference. Then you receive this guy, okay? And then you subtract this guy, and then you estimate this one. So that's what they say. You estimate this guy, which is the G stream, and then you subtract that stream from the receive signal, then you estimate this guy. So you had to do a SIC receiver. Then you cancel the interference, and you receive this guy. So similarly, you continue, etc. So what this is doing is the D-BLAS architecture, D-BLAS convert the MIMO channel into a parallel channel, and a good time diversity code. Time diversity code mean your LDPC code or turbo code can use to conjunction with the D-BLAS to achieve a good outage performance. So I hope you understand what is this D-BLAS is doing, because the channel, this is for the slow fading channel. Slow fading channel, this channel is constant for longer time. So your coherent time is very, very large. So there's no plenty of time diversity. If it is fast fading channel, your big stream, the entire stream will go through different coherent time. You will get plenty of diversity, time diversity. But in the slow fading channel, your stream won't go through this time, channel is not going to change much, so you won't get the plenty of time diversity. So you need to get a different kind of diversity. How do we get different diversity? You split the data stream and send across antenna. So by doing so, your entire stream is going through, first half of the portion will go through H1, and the second half of the portion will go through H2, and so you will get a diversity. So that's what is about D-BLAS. So D-BLAS, with the successive interference cancellation, we will be able to get a good performance in the slow fading case. Any question? We will take a break. If you have any question, please ask me.
You are getting tired, sir.
No. I think 1 hour is the maximum we can talk, isn't it? So we started. Yeah.
Yeah, please sit, sir.
No. Any question we can discuss? So next, after the break, I will talk about multi-user MIMO downlink linear precoder.
Yeah, if you are having any doubts, please ask.
Okay, so that's what I explained yesterday. No. Okay, here, okay. So this is the channel capacity, MIMO channel capacity, okay. So as I said, this channel between the transmitter and receiver are random, okay. This guy is random. This channel H matrix is random variable, okay. So this guy is random variable. So log determinant in the capacities, this is a log determinant capacity, this is equal to C capacity, also random variable. Because this guy is random, so the C, this is a matrix random variable, but the C is a scalar, that is a random variable, okay? So when you take the expectation of that random variable, we talk about ergodic capacity or mean capacity. So that is the information theoretic measure for fast fading channel. Fast fading channel, we take the expectation of this capacity, mean capacity or ergodic capacity. But the slow fading case, we took the information theoretic measure, outage probability, and outage capacity. So what is that meaning is, so it's a slow fading channel. So and channel will take a one realization and stay constant for a long time for the slow fading channel. So you assume this channel can support, let's say, R bits per second per hertz, okay? You design a communication system accordingly. But let's say your channel is in very, very deep fade, and it won't support that R bits per second, then you are in outage. You are in outage because you design a communication system saying my system is going to support this R bits per second, but this H is very random, and it become a deep fade, and then the capacity of that channel in the case of deep fade is not going to support that you are R, that you are in the outage. Okay? So what is the probability of that event is going to be outage probability. Okay? So if you are given outage probability, let's say this is like a 0.01 or 0.01, let's say, mean you are taking 100 realization of the channel, one of them is outage, so 0.001, okay, 0.01, okay? So 100 realization of the channel you take, one of them is outage, so 0.01. So you put the outage probability 0.01 here and try to find the R using this equation. That is outage capacity, okay? Given outage probability, you go and find the R, that is outage capacity. So if you given R, the probability of happening that event is outage probability, okay? So if you are talking about slow fading channel, this is your information theoretic measure, outage probability and outage capacity. Any other question? Okay.
D did not comment. Yeah, please wait for 5 minutes. By the way, everyone signed in the attendance sheet, huh? Can you share the yesterday's papers?
Yeah.
Yes, sir, I forgot to ask.
Yeah, I know.
Please say, yeah, yesterday's code also, sir.
The code is in the laptop.
Which laptop?
Laptop I use.
Yeah, Mubina's laptop, okay.
Yeah. It is in the downloads file.
In the download.
Download folder. Yeah.
Yeah, I have to ask. Huh? Yeah? Okay. Okay.
It is in the download folder.
Yeah, I will send. In the downloads folder is there. Yeah, then I will send it. Yeah, please send today's slides and yesterday's slides.
Yeah, sure. Sorry? Yeah, 5G is, we use machine MIMO, and we use maximum ratio combining our maximum ratio transmission. This VBLAST is a kind of a MIMO architecture. It is implemented in the Wi-Fi system, etc. Yeah. Yeah, VBLAST. Yeah. Wi-Fi. Yes. Yeah. If it is a slow fading channel, your channel between the access point and you are not moving much, so it is going to be D-BLAST architecture will be.
Which one is more expensive?
I mean, MMSC is more complex. Zero forcing is not much complex. So order of complexity is MRC is less complex, maximum ratio combining, and then zero forcing is second, and MMSC. And then MMSC SIG this is a non-linear receiver. So the complexity is increased like this. So this is this is the nice proof. Maybe we'll do a question later on. This, how do we prove this one is? This is a nice proof. Yeah. Any other question?
Sir, you got what you asked before. Recorder, sir.
Precoder we are going to study in a minute. Okay. So this is what we are going to see, linear precoders. This one lead to messy MIMO. Maybe probably we'll talk tomorrow morning about that. But now we talk about multi-user MIMO, downlink precoding. So here, you know, we are talking about single cell here, single cell. There's a base station here with the multiple antenna and mobile unit. There are K users, let's say. The base station send a waveform that contain all user information. It will transmit to a downlink system users, and each of these users will extract its own information. Okay? So let's see if the base station is sending information to all of these users, but this user is not interested in any of the other user information. He is only interested to receive his own information. Okay, okay. But so if the base station is going to send normally one waveform which include all the user information, but this guy is only interested in his own information. Okay, so other user signals are going to be interferent to him. Okay. Okay, so that is called multiple access interference because each user receive all user data. So that is called multiple access interference. So to avoid that interference, the base station will do a pre-coding techniques. Okay, okay. So that's the one we are going to see. It will do a zero forcing precoder or MMSC precoder. Okay. That's what we are going to see, zero forcing and MMSC precoder. So MMSC and zero forcing concept is done at the receiver side, and you can do at the transmitter side as well. So we are going to look at it, the zero forcing precoder and MMSC precoder at the transmitter side. That's what the morning session is about, the receiver side signal processing. Now we are talking about the transmitter side signal processing. So in that case, we say precoder rather than the receiver architecture. Okay, we say precoder. So what this base station will do, it can do a zero forcing precoder or MMSC precoder. I will tell you what is this, how do we do that. If we do that, this guy will receive his own information only. It won't receive other information. So each of the user will receive its own information only if we do zero forcing precoder or MMSC precoder. And there's another one called MRT, maximum ratio transmission. This is the one is happening in the 5G and R with the messy MIMO case. Okay, so this slide set is not for messy MIMO. We will talk messy MIMO later on. In the 5G and R messy MIMO, we only do MRT, maximum ratio transmission is good enough. Okay. Anyway, so the story is, if the mobile base station send all the user information, this guy will receive all the user information. So that is causing interference. That interference is called multiple access interference. So to avoid that interference, this guy only wanted to receive his own information. Okay, so all the user information is coming here, but this guy wanted to get his own information and don't want to receive other user information. So this guy had to do interference cancellation, etc. So that will cause a lot of complexity to the mobile unit. So we don't want mobile unit to do a lot of signal processing. So that's why we do a pre-coding at the base station, All the complexity will transfer to pre-coding at the base station, and this guy will do a simple receiver. Then only your mobile phone will last for a long time. Okay, so that's why all the complexity is moved to base station, and we don't do any signal processing at the mobile unit. So that's the story about precoder. Okay. So this is the kind of a downlink processing. You have a binary data. So let's say the base station wanted to send some information to image or video. It is first changed to binary and then do a modulation and then do a pre-coding. That's what we are going to see, pre-coding. The base station will do a pre-coding and send it through the channel, and then your mobile unit will receive and then demodulate the information that you send here. Okay, so here the precoder, to do a pre-coding at the base station, you need to know the channel state information at the transmitter. TCSI mean channel state information at the transmitter. To do pre-coding, we need a channel state information. At the receiver also, receiver channel state information, etc., etc. So we need a channel estimation. So in general, precoder requires channel state information at the transmitter. Okay, so that's big asking. I told you the transmitter know the channel is a big assumption. Okay, receiver know the channel is okay. That's what happening in your 3G, 4G, 5G phones. But transmitter also know the channel is you are asking more. Okay, this is achieved by channel estimation and the feedback. So transmitter know the channel can be achieved by channel estimation and the precoder at the feedback. Okay, so yesterday I mentioned there are two modes of operation. One is called frequency division duplexing. Other one is called time division duplexing. Okay, so frequency and time division duplexing is called FDD and TDD transmission mode. Okay, so what does FDD mean? Okay, so here's the base station, here's the user, downlink user here. FDD mean uplink and the downlink are using a different frequency. Okay, uplink use different frequency, downlink use different frequency. So this is called FDD. Okay, so you have Airtel buy a frequency from the government, then half of the frequency is used for downlink and half of the frequency is used for uplink. Okay, so that is the FDD frequency division duplexing. In the frequency division duplexing, the base station will send the pilot signal to the user, and then user will estimate the channel and then feedback the channel to base station. Then only the base station can do pre-coding. Okay, so because the uplink and downlink are different frequency, so the channel will be different as well. So here, base station and mobile unit transmit on a different frequency. They are different frequency. Uplink and downlink channels are uncorrelated. Because they are different frequency, these channel, downlink channel and uplink channel are different. So to do downlink pre-coding, this guy need to know this channel. But this guy does not know the channel. What they do is send the pilot signal, and this guy estimate the channel and then feedback. Then only it can do a pre-coding. Pre-coding need a channel knowledge. Okay, but because this channel is different than this channel, so that's why this guy have to estimate and feedback. Okay, so this channel and this channels are different frequency. They are uncorrelated. Okay. Mobile unit need to estimate the downlink channel and feedback to base station, So this is a big resources consuming process, okay? So up to 3G and 4G, our system are FDD system, okay? And up to 3G and 4G systems are FDD system. We do TDD system also there, but mainly FDD system, so we spend more time on channel estimation and feedback, okay? Okay. But, okay, let me tell you about TDD system. So TDD means time division duplexing. So the same frequency is used for uplink and downlink, okay? So this is called TDD, but different time, okay? This portion of the same frequency is used for uplink and downlink. This portion of the time for uplink, this portion of the time for downlink, this portion of the time for uplink, etc. So this is called TDD system, okay? So this is base station and mobile unit transmit on the same frequency. Uplink and downlink channels are correlated. Base station can accurately estimate the downlink channel during the uplink reception, okay? So what this is saying is, here is the same frequency, uplink is, downlink is happening. So in the uplink, the mobile unit send the pilot signal, so this guy can estimate the channel. So that channel is same for downlink as well, because same frequency, okay? So this is called channel reciprocity, okay? So in TDD system, we have a channel reciprocity. Uplink and downlink are same frequency. So this guy don't need to estimate the channel and feedback, because during this training, this guy will estimate the channel. So same channel for downlink as well, because the same frequency, okay? So this is called channel reciprocity. So TDD is very famous in 5GNR, because in 5GNR, we have a large number of antenna, okay, massive MIMO here, okay, 64 antenna or 128 antennas are here. So each of the antennas, if we have large antennas, we have a lot of channel coefficient to estimate, okay, because we have large antennas, okay, massive MIMO here, 64 antennas. The user have a single antenna. There are a lot of channel coefficient to estimate, okay, 1H2 up to 64 channel coefficient to estimate and feedback. Then you don't have the coherent time. You will estimate the channel and feedback. Your channel is changed, so you don't have a time to do data transmission. So that's why there's no FDD massive MIMO base station deployed in the 5GNR so far. The FDD system is not there in the 5GNR, okay? So 5GNR, all the base stations are TDD, time division duplexing, okay? Because if it is massive MIMO, this guy will spend a lot of time. The coherent time is the time channel is constant, okay? Coherent time is the TC, the channel is constant. He will spend a lot of time to estimate the channel all this time, because there are so many channel coefficients. Then he had to spend some time to feedback. By the time channel change to different realization, so FDD system is not going to work, not successful so far in the massive MIMO case, okay? So, but up to 4G, we don't have a massive MIMO system. We have only 4 or 8 antennas, so we can do a FDD system successfully, okay? Any question? Okay, so that's the beauty of TDD. You have a channel reciprocity. Uplink and downlink is a same channel. So in the uplink communication, this guy will estimate the channel. That channel is same for downlink, so he can do a pre-coding. So pre-coding need a channel state information at the base station. So, okay, so now I'm going to talk about pre-coder, okay? So MIMO linear precoding, when employing receiver-based detection, multi-user detection causes significant computation burden for the mobile unit. So as I said, if you send all the user information, this guy had to decode his own information and cancel all other user information. This guy will spend a lot of signal processing power. So in order to avoid that, we transfer everything to base station. That's what this slide is saying. So mobile unit need to do channel estimation. We employed transmitter-based pre-coding, all the signal processing done at the base station. Less complex, mobile unit have a less complex, simple and cheap mobile body unit, okay? So this is, I already told you, all the signal processing is done here, and this guy don't do much signal processing that will lead to your battery will last for a long time, okay? So what is happening here, okay? So this is the MIMO channel. You can consider, we are considering a downlink scenario, but not massive MIMO. So let's say this guy have a 8 antenna or something like that, okay? Up to 8 antenna. So there are 4 users or something like that. Let's say 4 users. Okay, so so this is let's say M antenna and K users. Let's say normally assume M is larger than K, and even though these users are geographically different location, but you can for the time being for the modeling we assume these guys as a kind of a co-located. So the channel is going to be between here to here is K into M MIMO channel. Okay, even though these users are different location, you can put all these users as a co-located places. Then you can model the downlink channel as a K into M channel matrix. So that's what is shown here. This is the base station, have a multiple antenna. This is the receiver. Each of these antennas are considered as one of the users' antenna. Anyway, so we can still consider this is as a MIMO channel. Okay, increase capacity and transmission rate by use of spatial multiplexing. We saw that. Improve performance due to diversity, spatial diversity, interference between. Okay, so interference between channel antennas as well. So the received signal here can be written as this equation here. So this is the desired signal for the kth user. He is interested in his own information, desired signal. All other other user information from the downlink user, base station to others are considered as a interference. Okay, so now we need to do a pre-coding. So let's say this guy wanted to transmit all the user information is X. Let's say all the user information is X. It is going to multiply this X by a matrix called T. This is the matrix is called precoder. We will see what is that precoder is going to be. So it's given here for the zero forcing case. This is the precoder. So so we say the base station wanted to send all information. X contain all the user information. Before sending that information, this guy multiplied by a matrix. That is a called precoder. So to do that precoder, you can see that precoder is turned out to be like this. It need a channel knowledge. This channel knowledge had to be known. So that's why, FDD system, all the users estimate the channel and feedback, and TDD system, the channel is channel reciprocity is there. Anyway, so so we are going to find what is the T such that each of the user will receive their own information only. They are not going to receive other user information. So this is called pre-coding. Okay. So let's see. Matrix representation of the MIMO downlink receive signal. Receive signal is H index plus Z. Okay. So this receive signal is all the user receive signal are put together as a vector. Okay. This receive signal is all the user signals are put together as a vector R, and H, X plus Z. Okay. So what is the matrix T that minimize the mean square error of the receiver? So we wanted to find we wanted to find a T matrix that minimize the R minus X. Okay, we wanted to find a T. It turned out to be this optimization problem have the T matrix that is the zero forcing precoder here. Okay, zero forcing precoder here. So there is some scaling factor that will come, but we will talk about that later. So this is a zero forcing precoder that we saw similar to the zero forcing receiver that we saw earlier. So this is a zero forcing precoder. So the X is multiplied by T. That T guy is this one. Okay, you can see it involves channel. That's why we need a channel knowledge here. So if you do that, each of these users will get his own information only. Okay. So you can see this is the receive signal. This is the precoder T, X, H, and you can see the T is this guy. This is the T. Okay, this is the T. You remember the T is this guy, H Hermitian, H into H Hermitian inverse. This is the T, the precoder, zero forcing precoder. So the receive signal is, there is some scaling factor F, don't worry about that for the time being. H into the transmitted signal is Tx. This is the one transmitted signal. But now we know T is this. We know T is this. And if you see this one, this into this is identity matrix, and you will get this. So each of the receiver will get his own information. Okay, each of these. This is a receiver is a R. R is a vector contain each of the user information. R1, R2, up to Rk is put as a vector R1, R2, up to Rk. So each of the user will receive his own information, and because of the precoder, okay, hex, okay. So this is all about precoder. This is the MMS zero forcing precoder. No interference, single antenna perform for every single antenna performance for every antennas. However, the power of the desired signal is reduced due to factor F. This power reduction can be big, depends on the condition of. Okay, so there's because of this inverse, this H matrix had to be good channel. Okay, in other words, there should be a rich scattering between transmitter and receiver. Otherwise, if this guy become a ill-conditioned matrix, then inverse will give you some trouble as well. Okay, so if you have a rich scattering between transmitter and receiver, then this condition number of this channel matrix is good, is very close to 1, and then you don't have any problem with the inverse. Okay, so this is called zero forcing precoder. It is also called channel inversion precoder. Okay, there are many names. Okay, so it's the same as channel inversion precoder. Okay, so there's another precoder is called is similar to regular MMSC precoder. Okay, it's called regularized channel inversion. There's an additional term here, alpha into I. So this is the MMSC precoder. Zero forcing precoder, and this is a zero forcing precoder. And if you have, we are talking about regularized zero forcing, regularized channel inversion, or MMSC precoder is going to be some alpha into I will come here. Okay, so that's the difference here. So this is again turn out to be it's going to perform better because this channel inversion will be won't be an issue here because alpha into I. So the alpha can be, we can optimize the alpha such that it is increase the capacity or something like that. The alpha depends on does not guarantee a. Okay, so the scaling and all these things, the inversion problem will be eliminated by this alpha here. Okay. Any question? Yeah. No, not that. Okay. Or get their own information. Yes, that's what we prove here. You see here, because of this become identity, the receiver signal R1 is X1. Yeah, multiple user case. Yeah, it's downlink. Any other question? So up to 4G, we use this kind of FDD system, frequency division duplexing, do channel feedback, and do this kind of recorders. Okay, so here some performance curve. This is the simple error rate versus SNR. Okay, so there are two set of results here. One is the here is the 4 transmit antenna and 4 user. Other one is 10 transmit antenna and 10 receive antenna, 10 users. Okay, so you can see this one is for the 10 transmit antenna and 10 receive antenna, so 10 users. for the regularized inversion, channel inversion precoder, and similar case for the channel inversion precoder is there. Okay, so these two curves are for 10 antennas. Okay, these two curves are for 10 antennas. This is regularized channel inversion. This is zero forcing or channel inversion precoder. You can see this regularized channel inversion precoder performance increase, okay, improved. And these two curves are for 4 transmit antenna at the base station, 4 user at the 4 downlink users, and this is for the regularized precoder, and this is for the channel inversion precoder. So there is a performance different compared to channel inversion and the regularized precoder. Okay, any better performance? Yes, yeah, because of all these gain will come, diversity gain, multiplexing gain, all these gain will come, and we will get performance improvement. This is for the bit simple error rate. I will show you some capacity plot here. You can see this is the capacity. Okay, so this is the still we are far away from. Okay, so I'll tell you what. So this is the kind of a channel capacity, some capacity. Okay, channel capacity or some capacity, and this is the capacity for the regularized inversion channel precoder, and this is the capacity for the channel inversion precoder. Okay, you can see the regularization precoder is performing better compared to channel inversion precoder, but still there is a gap here. This gap can be closed by using dirty paper coding that I mentioned. Okay, dirty paper coding is similar to MMSE SIG. MMSE SIG. MMSE SIG we do at the receiver side. Similarly, we get similar to that in the precoder we call dirty paper coding. If you do that, you will go closer to this line. Okay, but this dirty paper coding is very complex. People have studied recently because of after machine learning, research. People are doing studied how to implement dirty paper coding using machine learning techniques. So that's one paper by Madhani as well. Ankit. Okay, so any other question? Yeah. Yeah. Okay. You want to note down or you want to see it? Explain. Any other question? So the TDD, FDD, you guys are happy? Yeah? Yeah, they can change the location, no problem, yeah. Okay, so every yeah. So these results are for one coherent time. One coherent time, the channel is constant and all the performance is done like that. Yeah, one coherent time we had to do channel estimation, feedback, and transmission, and another coherent time. The coherent time are still long enough to do all these things, even though the users are moving. Channel is not that much moved very quickly. So there is a coherent time to do all these channel estimation, feedback, and the communication. So this is the story. Single input, multiple output, multiple input, single output, then MIMO, point-to-point system, then multi-user MIMO like this, and then messy MIMO. So this is the way the story evolved. Okay, so 2G and things like that, we use 2 antenna base station, and we did a receiver beamforming, etc., transmit beamforming, 3G as well, space-time block code. And then the MIMO point-to-point system came specifically for the Wi-Fi scenarios. then that lead to multi-user MIMO in 4G, and then 5G become massive MIMO. Any other question? You want the next slide? Yeah. Yeah.
Capacity as well as the performance
Improved, yes.
improving
Yeah.
with increasing number of antennas.
Yes, yes, yes.
That is not the case in CI.
No, CI also going to be improved as well, but there is a performance gap. Yes. You can see, so here is M is equal to N. Antenna increase, the capacity increasing, but as you can see, yes, it's getting saturated, but normally increase. Yeah. So here is, this is for, yeah, you can see this is 10 users and 4 users. The performance will improve with the MIMO system because of the diversity and multiplexing trade-offs. Performance, yeah, gains. Any other question? Shall we do caching or MIMO? Huh? Okay, so we are planning to do something different now. Did you heard about edge caching? Edge caching, yeah. So what is edge caching is, I will give you a small introduction and then Navneet can present. Edge caching mean, this is again belong 5G research, okay, belong 5G research. So, so whenever, you have a base station here, users are here, let's say if there's some popular news came or popular video, movies are released, then if there's a popular news or popular video movies are released, each of the users will asynchronously download those news and the videos or movies, etc., etc. So the base station is connected to the core network here. Every time somebody requests the file, it had to go through backhaul through this core network and bringing to the base station and sending to this one. So every time user will request the same file, the popular file, again and again and again in a different times, then every time the base station had to go and get that file from the core network, some content distribution network or somewhere, and get it back and to deliver to the user. So people have seen this trend, and then this backhaul become very, very congested, very, very congested. So to avoid that, in the future cellular network, if there is a popular file, people are asking, again, it depends on the time and the location on the areas. The popular in, something in here is not very popular in somewhere else. So it's all dynamically, the popularity and everything is changing. So the base station do some, prediction, etc., and take that file and cache that video in the base station. That's called edge caching, okay? Edge caching. This is the edge of the network. It is cached that content, video or whatever, and whenever these guys has a request, it won't go and get the file. It will have it here and serve the user. This is called edge caching. This is one of the research area recently. Is again a lot of research have been done, how to predict at particular location and particular time what is the popular file, and then cache that file to serve the user. So something popular today may be not popular next tomorrow. So that's again machine learning techniques are used to predict those files and used to cache that one. So this is called edge caching to alleviate the backhaul congestion. Okay, so maybe Navneet is going to talk about some edge caching research happened in the recent years. I'll come back to tomorrow morning for the messy MIMO case. Okay. What do you want? This.
Should I present Kyrie or not?
Whatever you don't do go very complex. So these are current research, 5G research, belong 5G research.
So wireless edge caching is a part of 5th generation 5G. So what does it mean? Edge means, it means network edge. So for example, whenever you make a call or you download some video, so this is your mobile and it goes to some base station, and then base station is connected to another, and then we have routers are connected, and this is like the network of base station, and then we have content server. Okay, so this is the network. Okay, so edge means the network, the nodes that are directly connected to the users. Okay, if this base station is directly transmitting to this user, so this is called the edge node. Okay, so wireless edge caching means we are caching means storing. We are storing the content at the edge nodes. Okay, and we are delivering it wirelessly. So this is the outline of the presentation. So here we are presenting the dynamic caching. So dynamic caching means dynamic caching means the popularity of files that we want to store in advance are changing. So how do we store it? That is dynamic caching. Okay, so we first present the motivation and introduction to dynamic caching, then followed by system model. Then we present online techniques, online popularity prediction and learning. So note that there are two techniques here. One is prediction based techniques and second is learning based technique. And another technique is using the Q learning. Q learning is reinforcement learning technique. Okay. As professor have said already, as we evolve more and more, we have intelligent devices and we see a lot of redundant and repeated content request. Okay, so for example, if some movie is released next week on Friday, so what happens? If it comes on Netflix, many of the users will start to download that movies. Okay, so it will create redundant request to the network server. Okay, so to avoid that, we can do edge caching. So this redundant and repeated content request, what does it do? It limits the capacity of front haul and back haul. Okay, so that causes network congestion. Okay, and that causes network failure. Okay, at these routers and other base stations. Okay, because all the file will be delivered again and again, it will cause congestion. So to lower the redundant traffic, edge caching is one of the possible solution, and it's very effective. So when it is a peak time, we can directly deliver the content if we have the content stored. Okay, so for example, at night, nobody, I mean like after like 12 o'clock, nobody watches that much. Okay, so that is like off peak time. But in the morning or the evening time, it's like the peak time. Okay, so in the off peak time, we can download the content in the caches, we can update the content, and the peak time we can deliver the content directly to the user without going to the content server. Okay, that way we can save this bandwidth. Okay, that is the idea for edge caching. Okay. So given the content popularity profile, now what is content popularity? Now to model this problem, what we do, or what engineers do, is researchers do, we internet is like millions of files. Okay, so we only consider a particular set of file, let's say 10,000. Okay, and these 10,000 file, we find out what is the popularity of these files. Okay, we do not consider like infinite set of files. We only deal with particular set of files. Okay, so and those particular set of files will have some popularity. Okay, so that popularity between 0 and 1 for each file. Okay, so if 10,000 popularity, if we can write that in terms of a vector. Okay, so that vector will be called a content popularity profile for that particular set of library. So library is what? Set of files. Okay, so content placement and delivery have been optimized for various performance measures in literature. So if we have placed some cache here, okay, what we want, we have put our cost here to place the cache. So we want to maximize our cache hit rate. We want to place the content such that it should be used more and more. Okay, so what we want to do, we want to minimize the backhaul latency delay, we want to minimize the server load, we want to minimize the cache miss rate, or we want to maximize the cache hit rate. Okay, these are the popular measures to measure the cache efficiency. Okay. So here this picture show analogy to an inventory problem. So inventory problem you already know. For example, you have a grocery store and you want to store some content, but you do not know what is the popularity in advance. Okay, so for example, let's say some festival is coming, let's say Diwali is coming. Okay, if you are a popular businessman, you already know what is going to be popular in next day, then you will store that content. But if you are new to the business, you do not know that much. Okay, so you need to know what is the popularity in advance, but it is also possible the next day the sale isn't that much. Okay, so what I mean to say here is that the content popularity it is not known in advance. Okay, so the next day what content is going to be popular, you do not know in advance. What content is being requested by the user after you have cached is not known in advance. Okay, we will know after the next day. Okay, so that leads to the dynamic caching. So this content popularity profile is not known in advance and need to be estimated from past observation. So if you are a popular businessman, you will estimate what is going to be popular this much, and you know the surrounding area, how much shops are there and how it's going to be popular. Okay, so based on the past observation, you can estimate. And there are other approaches also, like deep learning based prediction that requires huge training data. And we have autoregressive based prediction also. We have linear prediction also. And there are other approaches like to learn the content popularity independently across content. Online policy for cache awareness, these are some references. And low complexity video caching, this is also one of the approach for only for video caching. And another approach is for user preference learning. We deal with each individual user and try to learn each user preference, and then we place the content in our cache. Okay. So did you understand the problem? Problem is we do not know the content popularity profile in advance, and we want to store the content. What content should we cache? Okay. So for the dynamic caching, if we are doing with learning, we need to assume some assumption. Okay. So assume the content popularity profile varying as a finite state Markov chain. Why Markov chain? Markov chain means it depends on the previous. So it means to say the popularity will not decrease abruptly. Okay. If some content is popular today, it will be less popular today or least popular today, and it will slowly degrade, or it will slowly increase. It will not degrade abruptly. For example, if a movie is released today, its popularity will decrease little by little in the upcoming days. It will not go abruptly, okay? So for assuming Markov chain, Q-learning approach have been presented, and there are also function approximation Q-learning approach are also there, and multi-agent approach are also there, and some deep learning based RL approach are also there. So they are different reinforcement based learning approaches. Okay. So now we present the system model for the geographical caching that we are going to use for the caching for these online popularity prediction and learning. Okay. So this is a very simple example here. So we have assumed the base station and the users are distributed as Poisson point process, PPP. Okay. Poisson point process means you take the for example, base station is distributed as Poisson point process. What does it mean? You take the number of base station as Poisson random variable. Okay. You generate that number and you place the base station uniformly in this area, that much number. Okay. So let's say I generated a Poisson random variable with some mean, let's say 10 or 7. So I placed 7 base station here uniformly distributed in that area. That is also random. Okay. Similarly, I can put the users. Okay. So lambda BS denotes the density of the base station. Similarly, I can denote the density of the base station for the users. And I assume base station and users have single antenna, and cache is available at the base station. So this example shows each base station has three sizes of cache. Okay. And content library is F, and these are the indices for those content. And assuming large number of requests, I can assume my true content popularity, PT is given by, so this is the content popularity profile in a vector form. So PT1 up to PTN for time t, and it should be sum to 1. So I have normalized it. So it will represent like a probability vector. Okay. So in this example, let's consider, let's say these colored users indicate that this user wants green file, and this user want a pink file, this user want green file, this one want gray file. Okay. And for example, this base station, it has this teal file, and this is gray file, and this is orange file. Okay. So if this user want green file, it will request to the base station which has the file. Okay. So nearby base station, this has the file. Although this base station is nearer, but this base station has the file, so it will deliver the file, not this. Okay. So this way we can associate the users with the base station. So this is the random content placement policy. So earlier we have the, what is the probability? This is the content probability. Okay. Now we have another type of probabilities. These are called the network caching probabilities. So these probability denote how much the base station holds the content. Okay. So let's say this probability QT1, this is for a whole network. Okay. So let's say this probability is, let's say 0.7. Okay. So it means, let's say we have 100 base station, it means 70% of the base station will have this first file. So we have n files here. So this probability is for each file. Okay. So this is the network caching probability. Okay. So these probabilities, one is P and one is Q. So P is from user side, this much content is popular, and Q is from base station side. It means what is the probability that the content is present at the base station. Okay. So this process represent, if you know these probabilities, how will you place the content, how will you generate a realization at the base station. Okay. So let's say if Q is given by, Q vector is given by these 0.9, 0.7, 0.6, 0.55, 0.45, 0.4, 0.3, 0.1. So I can represent like this, and this total will be sum up to L, and L is equal to 4, and we have how many files? 8 files. Okay. So I can, this total is up to 4. So I can divide this into 4, and I can arrange them in terms of this stacks like this. So first is like this, and second is like this, and third is like this. Okay. So I can take a random number and take a snapshot here. So what will I get? Blue, cyan, yellow, and red. Okay. So that way, if I want to place the content, I know these probabilities, but I want to place the content in the cache. So what content I should place in the cache according to these probabilities. So this is how I will do. Okay. I will make this kind of color diagram, and I will take a uniformly random number between 0 and 1, and I will take a snapshot here, and I will get this red, yellow, cyan, and blue. I will put those files in 4-bit station. Okay. Similarly, I can take another snapshot. Let's say if some line comes here, I will store this pink, yellow, green, and blue file. Okay. So if Q is larger, it means, let's say this blue is larger, so it means this file will be presented almost all of the base stations. Okay. So this is the way of placing the content in the cache of the base station. So this is the analysis for the SINR. So here, this user wants green file, and it will get the green file from this. Okay. And what other base station have green file? This one, and this one. So they will interfere with this. Okay. And rest of which will also interfere if they are transmitting, but their interference will be different. Okay. So from the Sylvaniak-Mackey theorem, we can analyze the performance from a typical user point of view, and that typical user, we can write the SINR for a given file, and for a typical user by this mod of hk square p rk to the power minus alpha. Alpha is path loss exponent, rk is the distance from here to here, and ifk and ifc. So ifk represent the interference from these red lines, those who have files, fh files. ifc means those who do not have the files, and sigma square is the noise. Okay. So this is the interference limited system where interference is much larger than the noise. So we have two goals here. So one is to maximize the average success probability. We can successfully deliver the content. And second goal is the prediction. So we can accurately predict what is popularity going to be. Okay. So what is success probability? Success probability is defined as the probability that achievable rate of a system, rate of a typical user exceeds the rate requirement. So we considered a typical user, that green user, and that green user have this much rate. If it exceeds some rate, that probability, the average of that probability will be given by the success probability. So that is for a particular file, GQF. Okay. So it depends on the caching probability. If we can average for all the files, it will be denoted as the average success probability. Okay. So this is for the success probability. Now for the prediction, we can define these measures that we want to minimize. Okay. So first measure is the prediction measure. So we want to minimize this error. Okay. Second is the observed and the expected ASP difference. ASP is average success probability. So this P is this is the same thing. Okay. So we are given this P value and Q value. These are the true value. Okay. These are not known in advance, but we want to compare how much we are getting close to it. So that's why we are taking this. We want to minimize this value. Okay. This measure. Okay. So the observed ASP difference is this value minus this, because we have observed P T hat, the estimated one. Okay. And here what we have done, this is the expected. So we have also put P hat star T, P hat T also here. Okay. So this is the expected. So these two are almost similar. If we can bound some one of them, it will other will also be bounded. So this is the lemma. So here in the lemma, what we did, we solved this expression. This is a very lengthy proof. You can see the paper. Okay. So we solve this and we get this expression. Okay, where A, B, C are the coefficient, depends on the physical layer parameters like number of antenna, transmit power, bandwidth, okay, and number of user, density of base station, okay, rate and bandwidth here. Okay, so this looks nice because these are very simple constant and we can now optimize this. Okay, so let me read. For a PPP network with interference limited scenario where the noise is negligible compared to the interference, the success probability for a typical user can be obtained as this. Okay. Now let's come to the techniques. So there are two techniques. One is prediction and second is learning. So first is the ASP maximization. Okay. So the ASP expression that we have formulated, derived in terms of A, B, and C, we can write the average success probability that is PS, that is in terms of PQ. Given the P, we want to maximize Q, and Q is the constraint with respect to cache. Okay, so if we maximize it, we get this expression. So this problem is non-negative least square problem. You can see the paper if you like. This is also a long derivation, and this algorithm also given there. So what we see here, so there are three quantities here. What does it denote? If content is very popular, probability is very, very high in P, we will certainly store the content. If probability is very, very low, we will not store the content. Okay? If content probability is like in middle, like 0.5 or something, we need to check. Okay? We need to do it intelligently. Okay? So we need to think about the probability that are in the middle. If content is very, very popular, we almost surely need to store it. Okay? Here you see one more observation is that this QF depends on this P bar. P bar is what? Square root of P. Okay? And these set R, P, and Z, it will depend on the threshold. When you solve this optimization problem, the threshold will come and it will be based on A, B, and C parameters. Okay? And the popularity measure, this probability, this profile P. Okay? So let's come to the prediction method. So in the prediction method, the first is the popularity prediction method. So here we consider a simple prediction method. So this is the linear prediction. Okay. So this equation says that at the time t, it can be considered as a linear combination of the previous D popularity profile. Okay. So here one thing you note, we consider C in R. Okay. It means if we consider C to be, let's say if we consider C to be positive, it means this P1 and P2. The P3 will come in the between. Okay. If P3 is outside, we cannot predict it if C is greater than 0. Okay. If C is in R, we can also predict P3. Okay. And this is the probability vector, so it should be sum to 1. So based on this, based on this dth order linear prediction model, given the tau observation, we can write the least square problem here. Okay. So this is the least square problem where the all coefficients sum to 1 and the predicted popularity at time t plus 1 is non-negative. It should be non-negative and it should be sum to 1. So it should be sum to 1. This constraint come here. Okay. So we solve this, we will get Ck and Pt plus 1. Okay. So this will be the prediction. So for this ppm, we analyze this delta t plus 1. So we get this expression. So what does it say? So there is this term coming and this P bar is coming. So it shows that ASP is close to maximum as CP of the mid popular content are close to uniform. Okay? So this comes, it shows that it should be uniform distribution, because if it is uniform, so all probability will be equal, right? So it means if it is actually equal to uniform distribution, it will be 0. Okay? Only for the mid popular content. Okay? So there were 3 sets here, R, P, and Z. So the third set, the middle set is P. Okay? Second prediction model is Grassmannian prediction model. Any question up to this point for this popularity prediction? ABC are the physical layer parameters. So it depends on the density of base station, bandwidth, number of antenna, and the rate requirement. We have covered this here. No, here. This A, B, and C. These are here.
Yeah, please explain that area term, sir.
These terms.
What is lambda base station?
Lambda is the density of base station, R naught is the rate requirement, W is the bandwidth, and this S naught is this thing, alpha is the path loss exponent, this is the integration, same thing here.
Another thing, sir.
Yeah.
Base stations are, you're considering small base stations are, macro base stations,
Small base stations,
small base stations.
small base station.
Service.
Yeah. So this is one of the prediction method. Second is the Grassmannian prediction model. So why this is important? Because if we have maximized this, okay, we note that this QF, the content placement depends on this P bar here and P bar here. So P bar is what? Is square root of P, okay. So square root of P, it depends, okay. So if we have some popularity vector P that is sum to 1, and if we take the square root, so it means this norm should be 1. So this vector P bar lies on the Grassmannian manifold, okay. So this leads to Grassmannian prediction model, okay. So from the optimization problem, it can be observed the positive square root of the CP maximizes ASP. So SCP means square root of content popularity vector. So this represents a line in the Grassmannian manifold. So similar to PPP, we can model the problem in linear prediction. However, this is P bar instead of P here, okay. And similarly, we can formulate the least square problem, but here we have norm here, and these are sum to 1, and it should be non-negative. Okay, so we can solve this using CVX. Okay, everybody know about the CVX, right? So let's come to the learning method. So the results of them I will show here in this next section. Okay. So online learning technique is like learning means we have to learn something that is fixed. For example, if you are in a building, if you are new to a building, you explore it again and again. You want to find something. You want to learn the pattern of the building. Okay. So it means you want to learn. You will ask some question. You will explore. You will make mistakes. Okay. So that is learning. Okay. So online learning is the process of answering a sequence of questions given maybe partial knowledge of the given knowledge of correct answer to previous question and possibly additional available information. So it means when you for example, you go to a building and you don't know what is the pattern and you want to reach let's say Kalpana madam office, you will not able to find it. So you will go again and again, you will ask somebody, you may also go to the wrong door. Okay. So it means you are try to find the answer of some question, whether I should go left, I should go right, I should go straight. Okay. So learning is performed in a sequence of consecutive rounds where at round T, the learner is given a question, that is let's say xt, and is required to provide an answer to this question, say the prediction PT. Okay? So after the prediction, the correct answer is revealed. Okay? So when you have found the Kalpana Madam office, your answer is revealed. You should have gone to left, you should have gone to right, then left, you would have reached there. The learner suffers a loss L, PT, YT. So Y is, for example, Y is a set of 0, 1 for online classification problem. So either, let's say, some classification problem you might have heard of, let's say 2 classes classification problem. So you can select Y equals to 0 and 1. So learner's ultimate goal is to minimize the cumulative loss suffered along its run, which translates to making few prediction mistakes. So it means you have to find the your answer as soon as possible. Okay, so for example, you want to learn the architecture of the building, how it is. You want to reach the Kalpana Madam office. So you want to minimize your mistakes. You have to find as soon as possible without making much mistakes, even if you are new. Okay, that is learning. The first approach in this learning is the weighted follow the leader. Okay, so here this is the problem for the weighted follow the leader. So what does it mean? So Wi represents the weight, and I am given this observation up to time t, and I want to predict pt plus 1. So P represent what? Popularity. So I have been given the information up to like time t, and I want to predict t plus 1. Okay. So this is my optimization problem. This problem is sum of norms. Norm is convex, so sum of norm is also convex. So this problem is convex. I can solve it. You can also solve using the pen and paper, using this by taking the differentiation, and you can solve this. You can come up with this solution. Okay. So this solution I can also write in terms of previous observation. Okay. So what this equation denotes here, so this is the true observation and this is the predicted observation. Okay. So the new observation, new prediction is equal to the weighted combination of the predicted observation and the true information. Okay. So W represents the weight, how much you want to weight that observation. Okay. You want to weight your prediction more, so you can choose W accordingly. And if you want to weight your actual prediction more, you can weight accordingly. Okay. So one way to choose weights is by this exponential function. Okay. So I choose weights like Wi equals to kappa t a to the power t minus I. So we have the constraint weight should be sum to 1. So if weight should be sum to 1, I can compute this value of kappa t equals to 1 minus a divided by 1 minus a to the power t. And if I choose a equals to 1, it means Wi equals to 1 by t. It means I am just taking the mean of the previous observation. Okay. If a is less than 1, it means it weights recent observation more. Okay. Is this okay? So regret. So in the learning, we calculate the regret. So the regret is defined by this. So at the end of round t, so learning happens in rounds, right? So at the end of round t, what is your regret? So if you are given some prediction p, so you can define your regret like this. If what is your actual minus what is your predicted, so that is your regret. I mean, for example, if you want to go to Kalpana Ma'am office, you would have minimized like this much, like this much of time, or and actually what could have been. So if you take the difference of those, that is the regret. Okay, and by this process you can bound the regret. So I get this OT. OT means it depends on the t. T is the number of round. It means as the number of t increases, my regret increases. Okay. So if we are getting less than OT, it is good. It means we are learning good. If we are getting more than t, it means we are not learning. Our error is increasing. our regret is increasing. Okay? So if we are getting less than OT, we are good. So for a equals to 1, we see that we are getting O log t regret. Okay? So up to OT or less than OT, if your algorithm is getting the regret OT or less than OT, it is good. Okay? So okay, these are a simple calculation. If you see the paper, you can find out details of each of the expression. Okay? So this is, I have written in terms of algorithmic format. So for each round, what will I do? I will choose the weight like this. Then I will do this prediction based on the previous true observation and the predicted observation. Then after I have predicted, I will observe this. Okay? So this is like a grocery example you can think of. Like I have placed, after the next day, you will find what is the true content popularity after the end of day, right? So this is like after that you will find what is the popularity after your prediction, okay? So similarly, I can also calculate the ASP regret, which comes out to be OT. ASP regret is defined by like this, okay? So next algorithm, any question up to this point? Am I going fast? Okay. So the next question is, next topic is the weighted follow the regularized leader. So here, so this we maximize the ASP is average success probability. We presented one theorem. In that theorem, the content placement probability depends on the square root of content popularity. The similar observation leads to this approach, weighted follow the regularized leader. So if you have two vector in Grassmannian manifold, you can measure the distance between them using the caudal distance. Okay? So caudal distance is given by like this, dc square p1 p2 if you have two vectors, which is given by 1 minus, this is like the correlation. Okay? So minimizing the caudal distance is equivalent to maximizing the correlation, that is a cross product. Okay? So the learning problem, what we have maximized here, the weighted combination of these cross products. Okay? So this problem you can solve and its answer come out to be like this. Okay? Here you note that instead of this sum constraint, I have this norm constraint. Okay? Because this is square root. Okay? And weights you can select similar to the previous weighted follow the leader, WFTL. Okay? Any question here?
Sir, you told that you mentioned that you are using some deep learning algorithm.
Deep learning algorithm.
Somewhere
I'm using reinforcement learning algorithm. So deep learning I'm not using here in this paper. So I have these three methods here. One is the prediction method, second is online learning, and third is reinforcement learning. And reinforcement learning, I have also two other methods, function approximation and conventional learning. Okay. So for this formulation, we can also reduce it to this expression. So this expression shows what? It is like the weighted combination of the previous square root of content popularity and the predicted square root of content popularity. Okay? So this equation obtained from the trigonal inequality. So similar to the previous W weighted follow the leader, we can calculate the regret here, and it also comes out to be OT, and for a equals to 1, we get O log t regret. Okay? So this is the W4L algorithm, weighted follow the regularized leader. So we initialize with kappa equals to 0. For each round, we initialize with W, and we predict this, and then we normalize by this kappa t and observe the next observation, and so on. 1 minus a divided by 1 minus a to the power t. A we can choose 1 or less than 1. Between 0 to 1 we can choose. No, fraction values. This A is here, yeah, A is less than 1. We have weights like this. Yeah, I have chosen maximum value A is for 1. It means if we choose equals to 1, it means we are choosing just the mean of it. If we choose less than A, it means we are weighing recent observation more. If we choose like greater than A, it means we are choosing past observation more. I mean, we are weighting the past observation more. Okay, I mean that is like not recommended. Okay, so let's come to the simulation result. So we have considered movie lens dataset. Movie lens dataset is a set of movies, okay, where ratings are provided, dates are provided, and the timestamps are provided by different users, multiple of users. So we consider 1024 movies for our simulation, and we consider the content popularity profile obtained by the normalizing the rating across those movies. Okay. So if movie is rated that much, it means it is that much popular. So for prediction model, we choose fourth order model with 10 observation, and for online learning, we choose A equals to 1, and for these are the PPP parameters, Poisson point process parameter, lambda BS, W, alpha, R naught, and L. L is the cache size, 32. And for comparison, we choose two other methods. One is request prediction model. So we generate the random number of requests from user and try to generate using the use the auto-regressive model to predict the number of requests. That is an integer. So we predict the request in terms of integer, then we normalize it and compare it. And second is the mean guessing. Mean guessing is when we just take the mean of the previous request. Okay. This is the overview. Okay, so let's first see the result, then we go to the overview. So these are the all of the methods here. So autoregressive method is the number of requests we will predict by the autoregressive process. These are the FTL and 4L method. Mean guessing means we are just taking the mean of the dth order. Okay, and these are the PPM, GPM. Those are also dth order. So this method is good for the MSE minimization, and square root of content popularity is related to the ASP. So this is good for ASP minimization, and this is 4L will also include the square root of P. So this is also for the ASP regret minimization good, and this is related to the MSE regret. Okay, and this is suboptimal because it also relates to PPM. Let's say if we take CK equals to 1 by D, it reduces to this, okay, and it also relates to this one. Let's say if we instead of T, we take limited number of observation, it's also related to this. So this has the in-between performance of this. So this is the MSE and DASP. DASP means difference of ASP. So optimum value minus the actual achieved ASP value, okay. So here we see that, so for MSE, these two methods, orange and yellow, that is the GPM and PPM, that is the prediction method. OP methods, online prediction methods works well. And for the DASP method, we have this orange, that is GPM. GPM is Grassmannian. So Grassmannian performing good here because Grassmannian relates to the ASP minimization, okay. So it minimizes the ASP, okay. And the other are, so mean guessing is equivalent to trivial OP. I mean, if we reduce CK equals to 1 by D, that is trivial OP, online prediction, and suboptimal OL FTL. If we reduce the number of observation, it's related to that, okay. So these are the regret. So here are the rounds here On the x-axis is the round, and the y-axis, there is the MSE regret, there is the ASP regret here. So we want to minimize the regret. So you see here, we have this red line here. So for regret, we computed for what? Online learning algorithm. Okay, so learning should perform better here. Okay, so here we perform only single metric for overall, and here we perform regret. Okay, so prediction method should work better here, and learning method should work better here for regret. Okay. So here you see this red is OLFTL. OLFTL is working good for MSE regret, and here you see this green. Green is for 4L. 4L is related to the square root of content popularity. So square root of content popularity is related to the ASP minimization. So ASP regret is minimized by this green curve. Okay, and OLFTL is also in close with this green curve. Okay. So why we have plotted this? This also show the trend. For trend means we said that this is OT and O log T. That thing we can also see. This is the log scale, and this is the T. If it is going very high, it means it is going larger than OT. Okay. So whatever we have seen in theory, we can also verify here. Okay, that's the purpose here. So this is DASP, difference of ASP versus cache size. So if we increase the cache size, what will happen? We can store more and more content. We can deliver more and more content. My ASP will be high. Okay, so difference in ASP will reduce. Okay, so difference in ASP is getting reduced. And here, so I'm choosing ASP difference. So this blue is for online so this is not regret. So online prediction method will work here, good here. So these blue methods are performing better here. Okay, online prediction. This is with respect to the content library size. If I increase the library size, what will happen? Okay, so our MSC is showing to decrease here, for and ASP difference is also being decreased here. Okay, and here I have chosen the cache to be half of the content library. Okay, so these are results for the content online prediction and online learning, two methods. If we have time, we can go for the Q learning also. We have time? Reinforcement learning.
What is the time complexity for these all?
Time complexity is these are online, so time complexity is very, very low. So you see here, so this is just one square root, one division here, and two multiplication, one addition here, and here one division here. So time complexity is not much. Okay. So that's why they are called online algorithm. Online means they can be deployed in real time with very less complexity.
Is it, you use this process to the online downloading?
Online downloading.
Yes, you said you use the downloading faster than the old one.
So these are for prediction and learning. So we are doing this P here. So P means prediction. So that downloading is a different part. So first we have to store in the cache at the base station. So that base station will store cache. When it will cache? At the off-peak period, when users are not downloading. So that part, so it need to estimate what it should do, what it should cache. Okay. So for example, you have grocery store, you will store the content when? At night or when in the morning, when users are not there, and you will store the content based on user request, whatever the content was popular the previous day. Okay, or you will estimate that. So what we are doing here, we are trying to learn based on the previous request, we are trying to learn what is the popularity of the content. Then we will place the content accordingly. Okay. And after the next day, we will observe what is the true popularity. Okay.
If you have energy, please tell
Yeah, okay.
If you have energy only.
Yeah, it's fine. So in the Q-learning, we adopt a similar model. So here we have chosen massive MIMO also, massive MIMO base station with single antenna users, and both are distributed as homogeneous Poisson point process. And each user is connected to its nearest base station, which has the file, desired file. Okay. So here we have considered only two color file here. Red means the file F, and the base station blue means other files. And this is the Voronoi region. You can plot in MATLAB, okay, if you want. So Voronoi region based on base station having FF content in their caches. Okay, so based on red, this Voronoi region is plotted here. So similar to the previous, we can use the Selvignac-Mackey theorem to analyze for stationary and homogeneity of the PPP. A typical user at origin can be considered for performance evaluation, and the typical user we can write the SINR equation where this is what? This is the desired signal power. This is what? This is the interference, inter-user interference, I mean like intra-cell interference. So one base station is transmitting to multiple users, so it will be intra-cell interference because it will contain the signal of all other users, and this is the interference from other base station. So this is interference from base station, those who have the same file and those who do not have the same file, and this is the noise variance. Okay. And W is the precoding we have used. So similar, professor have mentioned, we are using MRT precoding for massive MIMO base station. Okay. We can also use geo forcing also. So HK is the concatenated channel for the kth base station. Okay. And this is what? This is zero forcing precoding. You have seen that, right? So this is zero forcing precoding. If we consider zero forcing precoding, inter-cell interference get eliminated. Okay. So we will get this term. Okay. So here, this first term will get 0 if we assume zero forcing, and these three terms will remain. So I have combined these two terms here, and this is the noise term. Okay. And PT is the transmit power. If I assume MRT, my expression of W will be like this, and my SINR will be like this, and this term will be there, intra-cell interference. Okay. So this factor of M is the number of antenna. This is called the massive MIMO gain or array gain. Okay. So this factor increases the SINR. So this is important. Okay. You can see the details of each and every step in the paper also. Okay. As much you want, I can finish it early.
Yeah, I want the participants to learn at the same time. I told the other faculty members that
Okay.
yeah, they can interact with the professor at the project.
Okay. So what do you want? We can do it later, so if you want.
Yeah, please, I mean, okay sir, you also please learn.
We can do it tomorrow if you want.
Yeah, maybe you can sit with the professor and interact, sir, while it goes on with the. Yes, please take the professor to your room, sir. Sai Prakash garu. Okay, please take. Sai Prakash sir.
So here also we analyze the average success probability. So this is the success probability. Like previously, we have assumed single antenna in the online learning work. We have assumed massive MIMO, and the expression is same here, but the derivation is different because of massive MIMO. Okay. So we will get some expression of something of this kind. Okay. Where these are different details, okay? So you do not worry about these details. You only worry about this, the factor Q here, and how it is, how the noise and the transmit power are doing this, affecting this expression, okay? So for interference limited case, we can get nice expression here, QF divided by 2B, QF 2A minus 2B plus 1. So here the success probability is independent of the density of the base station and user. So that is an important observation. So why does it do? So it depends only on the caching probabilities here, and the reason is that the strength of the both desired signal and interference increase with the increase in the density of base station. So if we increase in the density of base station, it means base station comes closer and closer, okay? So base station comes closer, both the desired signal intensity and the interference signal intensity will also increase. So you have the SINR expression, right? So it means numerator will also increase, denominator will also increase. So ratio will not change that much, okay? So that's why this expression comes out to be independent of the density of base station and the users, okay? So this is the, so earlier we were getting some exponential here, okay? If we do exponential approximation, we can also simplify that expression like this, okay? So we will use this expression for Q learning also, and we will use this expression also for Q learning. So we will use this expression to propose a new method for Q learning, okay? So with this expression, we can find out the average success probability across all the files. So this is across one file, GQF, for the fth file. We can average, we can get for all the files, okay? So Q learning. So this is the terminology for the Q learning. So let me go quickly. So environment. So environment is a time varying system which upon taking action, it gives some observation and also gives some reward, okay? Agent is the actor who takes the action in that environment. State is a tuple of values which defines the instant of an environment. Action, it is a required input signal to reach the goal. If you have to go something, if you want to learn something, you have to take a step, you have to take the action, okay? So without action, there is no learning. Reward is a measure of states and action towards the goal. Discount factor weights the recent and future rewards, okay? How much you want to weigh your previous action, previous rewards, you can choose the discount factor, okay? So for example, your currency value today is not be the same tomorrow or after year, okay? So that is the discount factor. So let's say 1 rupee value, let's say 10 years ago, it has much of a value, but 1 rupee today doesn't have any value that much, okay? Transition probability means going from state 1 to state 2 when taking action A1. That is the transition probability. And there is another term called the state value function, which is defined as the set of actions starting from the present state S0, and this is defined as the cumulative sum of discounted rewards given the starting state S0, okay? And we can use the Bellman equation to find the Q function. Q function is what? The state action value function, okay? And people also call it critic function, okay? So Q function, for the optimal value of Q, we can find out like this, okay? So this is based on expectation. So its true value we do not know, okay? We can only estimate its true value, its optimal value. So if we have optimal value, this Bellman equation will be true for that, okay? So we can also define the temporal difference. This is the instantaneous reward and this is the Q value, okay? If we take the difference, we will get the temporal difference, okay? So this is just a toy example for Q learning. You can also find this in MATLAB also, okay? You can also try to write your own program in MATLAB using this. If we have time, I can explain, or I can skip it, or go to my results.
Sir, I am again and again and I am asking
Uh,
if you have energy.
yeah.
If you have energy, explain, otherwise please translate, sir.
Okay. Okay.
Yeah, sorry, he's fasting today, that's why I'm asking again and again.
It's fine. It's fine. It's fine. It's fine. It's fine. So you have time, right? I am asking only for time. Okay. So here, this is the system here. So you have 5 cross 5 grid. Okay. So you are starting from some random state and you want to reach at the terminal state. Okay. When you reach the terminal state, you will get the reward plus 10, and these are the blocks that you cannot cross. Okay. These are the blockage that you cannot go. Okay. And this is your, let's say, agent. Okay. So agent begin from cell, let's say 2, 1, and agent receive a reward of plus 10 if it reaches the 5 cross 5, that is blue. And agent is blocked by obstacle, that is black cells, and environment contains a special jump. So this is the special jump. Okay. So I have also programmed for this. If you want, I can also show you. Okay. So I can go from here to here if I will get plus 5 reward. Okay. And all other action result in minus 1 reward. If I go from here to here, here to here, I will get minus 1 reward. So Q matrix, we have to learn a Q matrix that will be 25 cross 4. 25 is what? Number of states. 4 is what? Number of actions. I can go north, east, west, south, up, down, left, right. Okay, 4 actions and 25 states. We can have 25 states, and these we cannot go. Okay. So Q learning is a trial and error based learning process. Okay. We also take random action, we also take greedy action, and we learn. So where sequential decisions are taken to reach the goal. So model free means it doesn't require the model of the environment and can handle problem with stochastic transition. It means random transition, and rewards without requiring adaptations. So minimizing the square TD, TD means temporal difference, that we have shown here. Okay, this slide. If we minimize the square TD by gradient descent, it will give us the Q update equation. So finally, what we have to do in Q learning, we have to find these Q values. Okay, Q values for each state. So here in this, my Q matrix is 25 cross 4. So if I find this Q matrix for 25 cross 4, I will find in each state what action I have to take. Okay. So let's say I am here, Q2, 1. So this will be, let's say 1, 2, 3, 4, 5, 6 entry. So in this matrix, 6th entry, I will have 4 values. I can choose that value accordingly. Whatever the value is maximum, I will choose that value to go to that action. Okay. I have to go left, right, up and down, so that I will reach my terminal point as soon as possible. That is learning. So this is the update equation. So what I am writing here, Q, this is the state, okay, and this is the action, this is for time t, and this is for time t minus 1. So this is the update equation, okay. So plus beta t. So this is the gradient descent. So this value is given by like this. This is the temporal difference. Okay. So this is what? Reward plus discount factor max with respect to A, Qt minus 1, this value, the previous state. Okay. Now this is the next state. Okay. And Qt minus 1, 2, 1, 2. Okay. So 2, 1, I am taking action 2. Okay. So 2, 1, I am taking action 2. 2 means south. So I will went to 3, 1 state. Okay. So this is the next state. Okay. So this is the process of Q learning. So what happens here? First we initialize the Q values. So 25 cross 4 matrix, I will initialize to 0. Okay. Then for each episode. So I have given an example for, let's say, building. You want to learn the pattern of a building. You go one time, for example, you want to find the Kalpana Madam office. So that is like the terminal state. Okay. Your starting point is the gate. Okay. You went and you go around, you go to the third floor, fourth floor, fifth floor, sixth floor, and you somehow went to Kalpana Madam office. So that is your one round complete, okay? So that is one round, and you, when you do this round multiple times, you will learn, okay? So this is, that round is also called the episode, okay? In one episode, how much you are learning. So I have run for some episodes here, and for T equals to steps. So when in each round, you will take some steps. You will knock at the door, is this Kalpana Madam office, or you will see something, okay? So that is the taking steps. You have to go left, you have to go right, okay? So that is like taking steps. So in each episode, in each round, you will take the steps, okay? And now those steps, let's come to those steps. How will you choose the step? There can be two possibilities. Either you choose greedily or either you choose random, okay? So this is the random step. So U means uniform distribution between these all possible action. I can choose uniformly with probability epsilon. So that's why this type of action is called the epsilon greedy action. Okay? So it means you want to go randomly. A second thing, you want to go greedy. Greedy means whatever the information you have, you will go according to that information to maximize the Q value here, okay? So you will choose that action. So here, one is exploration and one is exploitation, okay? So there is a trade-off between exploration and exploitation, okay? So this factor epsilon controls that trade-off. If I make this epsilon larger, it means I am taking more random action, okay? If I make it smaller, it means I am taking more greedy action, okay? So when we are learning, we have to control that epsilon accordingly. So in larger episode, we can reduce the epsilon, and the earlier episode, we can make the epsilon larger, okay? To learn more efficiently, okay? So after we have taken action, I will go to next state. So for example, here I have taken some south action. I will go to 3, 1, and then I will get some reward, -1 here. And then after getting reward, I will update my Q value using the equation that I have shown earlier, okay? So this is the process, and after that I can update my epsilon also, I can update my beta also, okay? So this is the process for Q learning development. So this is conventional Q learning, okay? For this also, I have code also, simulation also, I can show you, okay? Now for edge caching. So edge caching also happens in time slots, okay? So there are 3 time slots here. One is content delivery. Any problem? Okay.
Continue. How many of you want to go for lunch immediately?
Not for immediate, but it's a next topic. So I will go to the next topic. So,
How much time it takes, sir?
10, 15 minutes.
What do you say?
wait,
Okay, I mean, let us stop here because, yeah, even though he's not telling, I feel, what to say, pity for him.
Okay, we will in the next class, maybe I can show you the code also tomorrow maybe,
Yeah,
and complete this also, okay?
Tomorrow you please handle.
Yeah.
so we will expect the simulations on the wireless communication channels presentations.
Yeah. Afternoon session we will show on.
Afternoon session is mine, no?
Yeah.
So tomorrow,
Yeah.
in his session, you can answer.
Yeah. Actually,
Because yesterday I have asked.
no, this is actually a part of 5G communication. So edge caching comes a part of 5G. So that's why we choose this topic. Yeah.
You have asked him yesterday, I mean, I informed them that you are more oriented towards research instead of teaching.
Yeah.
Yeah, that's why they are preferring this. Or you want to go for teaching side only?
We have many topics for 5G also, like full duplex also, integrated sensing communication also. But if we present those topics, you hardly some, nobody may be able to understand, maybe. One or two of you maybe, partially.
Yeah, what do you say? Participants, please reply to me. You want them to go to one side or you want వినపడుతుందండి? ఓకే. Okay, how many of you know about water filling algorithm? Yeah, professor have already discussed about this water filling algorithm yesterday or day before yesterday. So should I explain about it or should I continue with the next things? Yeah, because now I mean, how many of you don't know about water filling algorithm? Yeah, I will tell you in which way you can write the research papers for this simple thing. Is that okay for you? Okay then. Water filling algorithm means, let us say, yeah, the cell phone is there. The cell phone is having a battery power of 0.5 watts. So, but at the same time, the cell phone has to send the signal. So, how much power that cell phone can use to the maximum extent for that video transmission or for talking to the base station? Yeah, whatever battery power is there, only that battery power only it can utilize cell phone. Or if you say, the cell phone is there, the cell phone is sending a video over the Bluetooth, this cell phone is sending a video over the Bluetooth to the other cell phone, let us say on ISM band. So, again Wi-Fi access point is sending its signal to the laptop. Remember, Wi-Fi also uses ISM band as well as Bluetooth also use the same ISM band. So, from the cell phone, if it is sending a Bluetooth signal to the cell phone will be creating interference to the laptop that is getting Wi-Fi signal. So, we have to control this interference also. Or we have to send the signal from the cell phone to the base station with the with the existing power only, with the existing battery power only. That's what is water filling problem. Here I am telling you again. So, how much capacity we can bear? How much capacity we can pass the signals? With how much data rate we can send the signals over any channel? That's what I am talking now. Yeah, for example, here this pipe is there. This pipe is very thick. Because it is a thick pipe, through that thick pipe, we can send signals, we can send water with more flow. More amount of water can be sent through this pipe. Whereas here thin pipe is there. Thin pipe is there means through the thin pipe, we can send the water with the lesser flow only. If we send the water with the more flow, what happens to that pipe? it will burst out. So we can the channel having a smaller channel gain can't carry more amount of data. If we try to send more data, what happens? We will be getting more bit error rate, more bit error rate. Or here thin pipes are there means it can't carry the water with more flow. Our pipe will burst out if we are sending the water with more flow. Same thing, here channel is there with a smaller channel gain. So this channel having a smaller channel gain can carry the data with smaller data rates only. So again, capacity I am talking about. So C equal to, this you may know equation, Shannon capacity formula. Shannon capacity formula is, yeah, capacity or maximum data rate that can be passed through the channel. C equal to B log 2 1 plus SNR. SNR is nothing but PH by sigma square. Here PI HI by sigma square means, here HI is the channel gain or fading, amount of fading it is having or amount of channel gain it is having. Sigma square is the additive white Gaussian noise or noise that is there in the receiver parts. So here, up to this everyone understood? I mean it is normal things only which you already know. So I have taken one simple problem here. So here capacity, let us say that Xi equal to 1 value. Xi equal to 1 value, please don't take Xi. Please don't take Xi. So sigma Pi less than or equal to Pt. If you try to explain this equation, that means that we are having M channels here. We are having M channels here. Over ith channel, we are sending Pi amount of power. We are sending Pi amount of power. So Pi amount of power means if you take Xi equal to 1, so total amount of power that you are sending, total amount of power yeah, let us say cell phone over the ith channel, it is sending Pi amount of power. How do we decide that Pi, you tell me? How do we decide that Pi power? Let us say that the channel instead of water, take it as a power. If channel is able to, channel is having a more channel gain, then is it beneficial to allocate more power or is it beneficial to allocate lesser power? If channel is having more gain. So here, if channel is having more gain means, more channel gain means, then the channel is able to bear, channel is able to have more data rates. Channel can have more data rates here. Please see here. This you take it as a channel. Let us say you are traveling, if you are traveling, you can carry 1 kilo, 1 kg luggage. But instead of carrying 1 kg luggage, if you are carrying 1.5 kg luggage, what happens? You will be tired. In the same way, or instead of carrying 1 kg luggage, you are carrying only half kg luggage. Then you will be traveling with more comfort. In the same way, here channel having a more channel gain can carry more data. Here it is more data rate. More data it can carry. Similarly, channel having smaller channel gain, it is having a small data rate here. It can carry only small data. Because channel having more channel gain can carry more data, how much amount of power we can allocate there? If we allocate more power, obviously, if we allocate more power, please see here. So capacity is proportional to Pi value here. C equal to BA log to 1 plus PI HA by sigma square. So capacity is proportional to PI value, log of PI or PI. So if you are allocating more power, then what happens to the data rate or capacity? Capacity also will be increased. But we increase the capacity, we allocate more power based on channel gain HI. Anyway, the channel having more channel gain can carry more data. That's why we try to allocate more powers here. We try to allocate more powers here because the channel can carry more data. Whereas the channel having lower channel gains, we try to allocate small powers so that bit error rate also will be small at the end, at the receiver. So that is what is water filling algorithm. So here we are allocating, so over the mth channel, so here I equal to 1 to m channels are there. So over all the channels, over all the m channels, how much power we can allocate here for all the channels, for all the m channels? Remember, this battery is having 0.5 watts only. How much amount of power we can allocate for the data transmission from cell phone to the base station? Only 0.5 watts. That means P1 plus P2, etc. up to PM can be less than or equal to PT. Here PA is the power allocated over the ith channel. So over all M channels, we are allocating P1 plus P2 plus etc. up to PM. The total combination of powers should be less than or equal to PT. Here PT is the total amount of power that battery is having. So that is regarding second equation. First equation you know. This WA can be taken as bandwidth or bandwidth for the ith channel or something you can take. Here Xi can be interference related to this. How it is related to the interference means I have already told you. So here power allocated. So it is creating interference of, let us say, so VI, PI, interference is created to the laptop. Once the cell phone is sending PI amount of power to another cell phone over the Bluetooth, but because of same channel usage, the cell phone is creating interference of VI, PI. VA or XI, okay, XI, PI. XI, PI amount of interference is created to the laptop there. So that XI can be taken as channel gain over the interference. Channel gain of the interfering term. Everyone understood these equations? So with the available power, we have to maximize the capacity that is sent to the receiver, and at the same time powers are to be more than 0. Is there any doubt in these expressions? This is the generalized water filling. I mean, now I am going to solve this water filling problem. How to solve the water filling problem means, how to solve the water filling problem means, let us say here they take the, for such type of constrained optimization problems, what they try to do is, they try to take, here we have to maximize capacity with respect to sigma equal to 1 to m, xi pi less than or equal to pt. Again, pi greater than or equal to 0. So for solving them, they try to take it as, so some Lagrange multipliers. For those who don't know, I am explaining now. They take Lagrange multipliers here, Lagrange multipliers equation. Whatever equation you are trying to maximize or minimize, they try to take that, and some lambda parameter or something they take, some parameter. I will explain the significance of that lambda value. Lambda multiplying with sigma xi pi minus pt. Meaning that, let us say that you want to optimize the performance. Optimizing the performance means, for example, when you go for tea, if they are offering biscuits, you will feel little bit happy. But instead of offering instead of offering biscuits, if they are offering you samosa or something, you will feel more happy. So how much proportionately you are trying to decrease this value? How much proportionately the left hand side term is close to the right hand side term? That proportionate term is decided by this lambda value here. So how they try to do is, they try to differentiate with respect to 0. Why they try to differentiate means, they want to find out, for example, we want to maximize something or we want to minimize something. So how do we do this? By doing differentiation, we try to find out the maximized value or minimized value. So by doing some sort of like this, by doing differentiation, we try to find the maximum value for the data capacity, or we try to minimize the interference there. So by doing this, you will be getting the equation as, if you don't understand, please ask me. You will be getting the equation as something like this. By doing differentiation over the powers there, over that parameter there, we will be finding out, you will be getting this equation. So this is nothing but Wi xi lambda minus ni. What is the meaning of this means? Pi plus means maximum of pi comma 0. Maximum of pi comma 0 meaning that, this is the meaning that pi should be greater than or equal to 0. You tally, if pi is a positive value, maximum of positive value comma 0, that pi value will be coming. If pi is a negative value, if at all in the calculations, if you are getting negative powers, so maximum of negative power comma 0, that means power will be 0. That's why this is the pi greater than or equal to 0, meaning that maximum of pi comma 0. So this can be written as 1 by lambda minus some ni bar, minus some ni bar. Same thing. Now how much power we have to allocate? You tell me, how much power we have to allocate means, what I have done is, if at all noise is increasing, then I have to allocate with smaller power. Why I want to allocate a smaller power means, because anyway noise is more. Remember the channel having very small capacity. Channel having very small capacity can carry only smaller data, because we don't want to have more errors. That's why we try to allocate smaller powers when the channel is having more noise or lesser channel gain. So same thing, if noise is small, we try to allocate more powers here, because the channel can carry more data. More data means we can allocate more powers. So this is the basic water filling problem. Now I will try to explain to you what is the water filling problem, how I have solved that water filling problem. So I have taken one glass there. Yeah, take it as one glass. In that glass, let us say that, yeah, this is N1 bar level, N2 bar level, N3 bar levels. N3 bar levels. Let us say that, yeah, that person, that pot making person or glass making person have designed the glass in such a way that the bottom of the glass is at different levels. Here glass is at N1 bar level, this is 0 on y-axis. Glass bottom is there at N1 bar level in this place, glass bottom is there at N2 bar place in this second place. Yeah, here glass bottom is there at N3 bar in the third place. So let us say that now you want to fill the water. How much water you can fill? How much water you can fill means, let us say that this is the total amount of water that can be filled above the noise levels is PT. Total amount of water that can be filled in this glass. Let us say this is the water that is there. Total amount of water that can be filled into that glass is PT, and the height of that water level is, we take it as 1 by lambda. 1 by lambda. 1 by lambda. Now tell me, how much is this? How much is this? This is 1 by lambda. 1 by lambda is the height of water level, height of top water level from the ground, from 0 level. So this is 1 by lambda. So above noise level, remember it is the bottom surface of the glass. It is the bottom surface, N1 bar is the bottom surface of the glass. So how much amount of power or water can be filled above that bottom level? Tell me. This is 1 by lambda is the height of the water level from the ground, and Ni bar is the noise level or bottom part of the glass. Ni bar is the bottom part of the glass at the height, height width or something. Yeah, Pi is equal to 1 by lambda minus Ni bar. So this is nothing but P1 here. This is nothing but P1 here from that equation. This is nothing but P2 here. This is nothing but P3 here. Please see this. More is the noise level. More is the noise level. Yeah, lesser power, because we are taking precautions such that only smaller number of bits gets errors. So here P1 is the power allocated for the first channel. P2 is the power allocated over the second channel. P3 is the power allocated for the third channel. Now what I have done is, instead of doing the powers like this, so what previous persons have done is, they try to initialize it to some value, some random value. For this random value, they try to check Pi equal to 1 by lambda minus Ni bar. For all I, they try to calculate powers and they try to check if Pi is less than or equal to Pt, or if Pi greater than or equal to greater than Pt, or if any power is going less than 0, or if any power is going above 0. What they try to do is, if it satisfies this and this, yeah, everything is fine. If it satisfies the required constraints, sigma Pi less than Pt, yeah, required constraint, if it is satisfying, okay. If it is a Pi greater than 0, if it is satisfying, then also it is fine. Then also it is fine. But if at all, for the calculated lambda, if it is more than Pt, or some Pi value is going smaller than 0, then what they try to do is, in this case, they try to increase it to previous lambda yeah, plus some delta value. Delta value also they try to take accordingly. Some known delta value. Some taken delta value. Yeah, again they try to calculate Pi equal to 1 by lambda minus Ni bar and they try to take if Pi less than or equal to, if it is greater than Pt, or some Pi is going less than 0. They try to check the taken constraints. If the constraints are satisfied, they will leave the loop. They will loop the for loop or while loop. If the constraints are not satisfying, again they try to increase the previous lambda with, they try to add the previous lambda with some defined delta value, and again they try to keep. Like that they keep on doing the iterations until all the constraints are met. They keep on doing the iterations until all the constraints are met. What was the drawback here? What was the drawback here? We started with some random value. If that random value turned out to be fine, within 2 or 3 iterations or within 50 iterations, everything goes well. If that taken initialized lambda value, if something bad happened, our guess is wrong. Our guess is wrong initially, then it means it keeps on iterating, it goes on around the loop, so many multiple times, thousands or lakhs or crores. So that is the problem. If it is going on taking more number of iterations, what is the problem here? If it takes more number of iterations, let me tell you. So let us say that base station is given with, let us say that the cell phone has to send the signal from 0 to t1 time. The cell phone has to send the signal from t1 to 2t1 time. Let us say that in TDMA mode, cell phones are communicating with base station. In TDMA mode, cell phones are communicating with base station. So what happens? What happens this? First of all, every cell phone have to determine how much powers to be allocated. In every cell phone, DSP algorithm will be running before sending the data. The DSP algorithm means solving this optimization problem. So that optimization problem means, so let us say that cell phone has to interact with the base station over this 0 to t1 time only. Second cell phone will be interacting with the base station over this t1 to 2t1 time only. In that case, let us say that, let us say that 0 to t1 minus delta time, it is allocating, it is doing power allocation only, it is solving Pi values only. So how much time is left for sending the data from the cell phone to the base station now? Only delta time is left for sending the data, from the cell phone to the base station. This is, I am telling as an example only. Here another way is there, if you think of it. So here what I am saying is, first of all, cell phone does the power allocation before transmitting the data. After doing the power allocation or after doing the channel allocation only, cell phone will be communicating its data to the base station. If it is taking more amount of time to do the power allocation or to solve the DSP algorithm, then in that case, very small time will be left for sending the data to the base station. So within that small amount of time, cell phone won't be able to communicate more data. That's why what they try to do is, they try to allocate powers as soon as possible. If we want to allocate the powers as soon as possible, then what is the method? What is the method? We have to reduce number of iterations, or we have to use closed form solutions. Closed form solutions there. So here we try to find the closed form solutions. Closed form solution means, let us say that sigma pi less than or equal to pt. Again I am repeating, our problem here is, in this water filling algorithm, the main problem is, if lambda is not taken properly, then it leads to more number of iterations. If it is leading to more number of iterations, yeah, comparatively data transmission will be taking very small amount of time. Yeah, within that small amount of time, it won't be able to communicate the data to the receiver. More data. That's why we try to find closed form solutions here. Closed form solutions means, for example, constraint here is sorry, sigma pi less than or equal to pt. So what is the optimum power? In which way we will get the optimum power? Tell me. Yeah, let us say 1 plus 2 is less than or equal to 6. 1 plus 2 is less than or equal to 6, or 2 plus 3 is less than or equal to 6, or yeah, another way, 1 plus 5 less than or equal to 6, or 3 plus 2 plus 4, 2 plus 4 less than or equal to 6. Which one will be giving more power allocation? Remember, we have to allocate capacity or data rate is proportional to the power allocated. If we want to maximize the data rate, we have to maximize pi value. Out of these combinations, which one is the most suitable combination here? 2 plus 4, more powers. 2 plus 4 equal to 6. Yeah, that's why instead of taking this, they try to take it as equal to pt. This is the best way to optimize the capacity or to maximize the data rate. So sigma pi equal to pt means, so pi equal to, already found out, 1 by lambda minus ni bar. Yeah, okay. Yeah, okay. This one is the one. Yeah, I forgot to mention W. Okay, anyway, similar equation. W multiplying with 1 by lambda minus ni bar. This is the PA equation with 1 by lambda. Here lambda is unknown value. Lambda is unknown value, or up to how much height we have to pour the water into the glass. That we know, that we don't know. Ni bars are known values, W's are known values. 1 by lambda only is the unknown value here. That means up to how much height we have to pour the water into the glass. So this one we have to find out, 1 by lambda. So here Wi multiplying with, so what we have taken, sigma pi equal to sorry, T vachinda. Okay. Yeah, within 15 minutes, please come back. Tea chalabaduddu, sir. I mean, asle meer feel avutunnaru, nenem pettatledani. Yeah, at least have tea, have hot tea. Yeah, please come after 15 minutes. We came to the conclusion that in order to optimize the data rate, we have to take equal to sign, sigma pi equal to pt. Yeah, again Pi equal to Wi multiplying with 1 by lambda minus Ni bar. Here 1 by lambda is the unknown value, or up to how much height? We have to drop the water, we have to pour the water inside the glass. So if you substitute sigma I Pi equal to Pt, sigma I Pi equal to Pt, so sigma I, Pi is nothing but equation is there, that equation we have taken, so 1 by lambda equal to Pt plus sigma equal to I value Ni bar by, I mean some equation in terms of Pt's and Ni bar. Yeah, actually we are using, we are having some m number of channels. Out of m number of channels, we are using only k number of channels. Why? Please tell me. We are having totally m number of channels. M number of channels. Yeah, here. But we are trying to use k number of channels only. Why? Yeah, let us say No sir, no sir. Yeah, I told you traveling example. If I can carry 1 kilo luggage, if I carry 0.5 kilo, half kilo luggage, then I will be fine. Yeah, but instead of carrying 1 kilo luggage, I am carrying 100 kilos. 100 kilos. Yeah, while doing gym also, instead of lifting the weight of 1 kg, you have lifted the weight of 100 kgs. So what happens? You will be collapsed down. So same thing happens here. Here, if noise level is there, yeah, let us say, noise level is so high for the second channel, so but you have poured the water up to this height only. Up to this height only. So this is the P1 part, power allocated for the first channel. This is the power allocated for the third channel. P1 and P3 are the power allocated. P2 is? Huh? Yeah, because noise is more, noise is more, we can't allocate any power there. Yeah, you are trying to lift 100 kgs weight for the second channel. That's why here P2 is 0. We don't allocate any power for the second channel because it is not able to carry any more data. Even single bit of data also it is not able to carry. That's why we don't allocate any power here for the second channel. Yeah, similarly here, that's why instead of taking all M channels, we are taking only K channels only here. K channels only. So what we have done is, here noise levels, we are arranging noise levels in ascending order. Once noise levels are in ascending order, powers will be in descending order. Yeah, if noise levels are increasing, powers will be in decreasing order. That means that here, this is a P1 value, this is a P2 value, this is a P3 value. So here, N1 bar less than N2 bar, less than N3 bar. Once I am arranging the noise levels or channels in the ascending order noise values, then in that case, P1 will be more than P2 and P2 will be more than P3. So once noises or channel gains are arranged in ascending order, powers will be coming in descending order. That's what we have done. This is the original channel model, but the channel model we have converted it into the ascending order noise levels. So that P1 more than P2 more than P3. Something like this. So here what happens? Yeah, what happens here? PM will be 0. Here PM is last, I have told you out of M channels, we are using only K channels. So K plus 1th channel will be having 0 value. Please see, P3 is more than P3 is more than 0. P4 or Pk plus 1, Pk plus 2, Pm values will be zeros there. So last powers will be zeros. So here the thing I have to find here is K value. That K value I try to find. That K value how to find? So now I have found out lambda value initial. I will be finding out lambda values by finding K value first. This K value we are trying to find out now. So, but what happened here? So, Pi is more than or equal to 0. This is another constraint we have. So, Pi is nothing but Wi 1 by lambda minus Ni bar greater than or equal to 0. Wi 1 by lambda is nothing but Pt plus sigma I equal to 1 to K or something Ni bar divided by lambda. Let us take it as some J value. J equal to 1 to J bar minus Ni bar greater than or equal to 0. If you substitute after that, let us say that Pt, sigma Ni bar, this is K value. Sigma J equal to 1 to K, Nj bar minus K Ni bar greater than or equal to 0. Something like this equation will be coming. From these equations, how I try to do it now is, don't worry, I will show the MATLAB code after this. So how this equation I got, first I will go for K equal to 1. That means that I pour the water up to this level only. I pour the water up to this level. That means here K equal to 1. I am starting with K equal to 1. Up to this level only I am tallying. After that I am checking this equation for K equal to 1. For K equal to 1. Still that is less than. That means that still it is greater than or equal to 0. This equation I will be checking. Again I will be going for K equal to 2. Here K equal to 2 means, for the two channels we are allocating powers. For the two channels we are allocating powers. We will be checking this constraint. We will keep on increasing the K equal to 1, K equal to 2, K equal to 3, like that. How many channels, for how many channels, that same constraint will be satisfied. That same equation will be satisfied. Like that, I keep on increasing the K value until it is no longer satisfied, until that equation is no longer satisfied. So how many number of iterations will be coming? Maximum. How many number of iterations will be coming? First I am starting with K equal to 1. First I am starting with K equal to 1. Okay, this is good. This equation is satisfied. Again I am going to K equal to 2. K equal to 2. Maximum K value that satisfies that equation will be maximum K value. We are pouring the water here. Okay. Still sigma Pi is less than Pt. Let us say we have increased the K level to 3. Once we have increased the K level to 3, sigma Pi less than or equal to Pt only is there. So if we increase up to, let us say that we have poured the water up to this over the 4 channels. Over the 4 channels. Now here still sigma Pi is less than or equal to Pt. So obviously we will try to increase the K value until sigma Pi becomes equal to Pt. Until sigma Pi becomes equal to Pt. Remember, our main constraint is, we have to get up to total power should be equal to Pt value. should be equal to PT value, not less than. So maximum for how many channels we can, over how many channels we can allocate the power, or over how many noise levels we can allocate the water, we can pour the water here. Over how many channels we can pour the water here. Remember, we have taken M channels. M channels. So K equal to 1 first iteration, K equal to 2 second iteration, maximum iteration that it can go is up to M levels. So only M iterations only, maximum it will be coming. So instead of going for 1000 iterations or 1 lakh iterations, going for M iterations is always okay. Yeah, that's what I have done. Now I will show you the MATLAB code. Here NS, number of channels are taken as 64. Yeah, let me do this. Okay. Number of channels are taken as 64. NS equal to 64. Yeah, I have used this code for cognitive radio. Yeah, that's why I have taken it as a secondary user. NS means secondary user, number of channels. So variance, sigma square. Sigma square, noise variance is taken as, these are rough estimates only. Yeah, later PT, total amount of power. Total amount of power is taken as, less than 1 milliwatt or something. Around 1 milliwatt. Yeah, yesterday I have asked, na? Yeah, this is how we have to, this H is taken as, in the comments it is there. In H is taken as Rayleigh fading. What is the meaning of Rayleigh fading? Rayleigh fading, you know right how Rayleigh fading comes. We have to take the Gaussian distribution here. Rayleigh fading is nothing but Gaussian plus J, another Gaussian. Why it is Gaussian? Real part is Gaussian and imaginary part is Gaussian. Tell me. Huh? Yes, Gaussian distribution. Because please see, what is when Rayleigh fading comes? When there is non-line of sight. When there is non-line of sight from the transmitter to the receiver, so many obstructions are there, lakhs or crores of obstructions are there. In this path, signal is going. In this path, signal is going. In this path, signal is going. In this path, signal is going to the receiver. So here, each path is taken, each path is taken, each path is taken, each path is taken. If 1 lakh paths are there, combination of 1 lakh paths will give Gaussian. Remember, yeah, in the grade sheets also, you must be doing the grade sheets, right? How will be the grade curve of your class? Obviously, it should follow Gaussian curve. If you don't follow the Gaussian curve, means that committee members will reject your grades, saying that something is wrong with your grades. Meaning that, what is the meaning of Gaussian? Some average value is there, whether the student is passing above the average value or below the average value. That is nothing but Gaussian. Similarly here, when 1 lakh or more than 1 lakh number of signals are coming towards the receiver, combination of more number of signals will be producing Gaussian distribution. Yeah, that's why it is real part is Gaussian, imaginary part is Gaussian here. Yeah, this is what is Rayleigh fading. Rayleigh fading comes in the non-line of sight communication, or no line of sight is there between the transmitter and receiver. That means receiver is not able to see the transmitter directly, or transmitter is not able to see the receiver directly. When non-line of sight is there, then it is Rayleigh fading. If line of sight is there, then it is Rician fading. So because of more number of obstructions in between, we will be getting Gaussian curve for the real part, we will be getting Gaussian curve in the imaginary part. So how to calculate the amplitude here? How to calculate the amplitude here? Yeah, let us say C equal to A plus JB. What is the amplitude of C? Yeah, C equal to root of A square plus B square. That means that the amplitude of a Rayleigh channel, will be root of Gaussian square plus another Gaussian square. Yeah, that's what I try to take it here. Yeah, please see this. That Randon produces, yeah, Randon means Gaussian distribution, normal. N means normal distribution. So Randon produces normal distribution. Here number of channels taken are NS. So Gaussian distribution or normal distribution for NS channels. Again, square root of minus 1 means imaginary part. Square root of minus 1 means JRI. Again, another normal distribution is taken after the imaginary part. After square root of minus 1, Randon is taken, that is another Gaussian. So Gaussian plus J multiplying with another Gaussian. So how will you produce the Gaussian channel, Rayleigh channel here? Please see this. It is a square root of, H is nothing but, channel gains is nothing but square root of real part of H square, Gaussian square plus imaginary part of H square. So this is nothing but a root of Gaussian square plus another Gaussian square. This is the H is nothing but here is the Rayleigh fading channel. This is how we produce Rayleigh fading channel. Yeah, but here, don't ask me why I have taken this, because I am producing a better result in this way. Here for exponential distribution, here channel gains I have taken it as exponential distribution. That is another matter. Simply for proving that my results are better than other results, I have taken exponential distribution. Yeah, similarly Debye values also. Similarly, Debye values also, here please see this. Wi values also have taken some random values, Xi values also have taken some random values. Yeah, here Debye values also have taken some random values. Here please don't worry about this. Yeah, I will go to my thing. Should I tell this? So this is iterations, it takes a long time. Okay. Yeah, they are initially taking K equal to NS values. NS means the total number of channels that are taken. K equal to NS values. Here I am going, I have explained from bottom to top, K equal to 1 to K equal to 1 to K equal to M values I have taken on the board. Here I am in the MATLAB code, I am going down. K equal to M value I am taking first. K equal to M value I am taking. Here please see this, K equal to 64, 64 channels I have taken. K equal to 64 I have taken 1 by omega, 1 by omega means 1 by lambda, 1 by lambda on the board. 1 by lambda on the board is nothing but Pt plus sum of V and NIO. V and NIO is nothing but, yeah, don't worry about this. This is NI bar. This is NI bar. Please check 1 by lambda equal to PT plus sigma NI bar divided by, yeah, some value. Here I have written it as, yeah, let me write it properly. Sigma double I. Yeah, PT plus sum of NI bar, sum means here sigma divided by, here it is nothing but sum of double i's in the denominator, sum of double i's in the denominator. After that, what we are doing is, for the calculated 1 by omega values, now what I am doing is, I am sorting NI bars here. I am sorting NI bar. Sorting is nothing but it arranges NI bars in ascending order. Remember, we are arranging the noises in ascending order. So in ascending order we are arranging it. Once sorting is done in the ascending order, what we have to do is, once we have arranged the NI bars in ascending order, then we are trying to find out the indices. What we are doing is, yeah, let us say that NI bars are equal to 152 is there. So here what I am doing is, NI bar sorted orders, they are taking it as 1 to 5. In which index arranged the noises in the ascending order, we have to sort double i's also in the same order, right? So here this is nothing but yeah, please see this. After sorting this, everything is coming in ascending order noises. Yeah, first one is 10 to the power of minus 5, second one is 10 to the power of minus 4, third one also 10 to the power of minus 4. Yeah, later 10 to the power of minus 3. That means noises are arranged in ascending order here. After that, here we are trying to find it in, here we are trying to arrange it in here. What happened? This index is nothing but sorted order 132. 132 is the index values. So into that index values, yeah, let us say that WIs are there. So for the channel, yeah, for the channel 1, W1 is yeah, some 1 value. For channel 2, W2 is some 5, yeah, let us say 10. For channel 3, W3 is 4. Here we have arranged the noises in ascending order. Here the channel WI values also we have to arrange in the same order, right? We have to arrange in the same order, na? That's why everything related to the channel, every other parameter related to the channel are arranged in the same ascending order, same index order. So this is the index is nothing but how we have done the ascending order. So into the same ascending order, we are arranging this. Yeah, this Ni0 values or Wi values. Yeah, next thing. We are going into this one. We are, yeah, next thing we are checking. Yeah, please see this diagram. Please see this diagram. Yeah, let us say that Wi Ni bar minus Wi2 Ni bar 1. So I am checking Wi Ni bar I means here I equal to 1, right? Yeah, let us say 2. 2 means Wi2. This is W1, Wi2. This is W3. Yeah, let us say that up to this level water is poured. Up to this level water is poured means, yeah, this P1, P2 part. This entire area, I mean, in that case W1 is to I Ni bar I. W1 N1 bar. Yeah, if we take I equal to 2, yeah, W1 W2 W1 plus W2 W1 plus W2 N2 bar minus W individual one W1 N1 bar W1 N1 bar plus W2 N2 bar. What it indicates? Tell me. Which area it indicates? Left hand side area, how much? Right hand side area, how much? Please remember, each channel width is taken in terms of W's, height is taken in terms of 1 by lambdas. So here W1 and 2 bar, W1 and 2 bar. This is W1 and 2 bar. This is W1 and 2 bar. This area is nothing but W1 and 2 bar. Please see this. This is W1. N2 bar is up to this one. N2 bar is up to this height. This is W1 and 2 bar. W2 and 2 bar. W2 and 2 bar means this is W2 and 2 bar. This is nothing but the left hand side area. Left hand side shown area. If it is, yeah, again, right hand side shown area. W1 N1 bar, W2 N2 bar. This is nothing but W1 N1 bar. This is nothing but W2 N2 bar. Please try to see how much area, after subtracting this area from this area, which one will be left out? Please tell me. Which one will be left out? This is nothing but this part. That part. Everyone understood, right? We are checking now whether it is equal to PT or not. Whether it is equal to the total power or not. Yeah, please see this. For all the K values, I am checking. Yeah, time is getting over. I have to finish this. What happened? Okay, please see this. What is the meaning of this? Please tell me. What UIO means 1. UIO means 1. Pi t of 1, if it is less than pt, and pt is less than pi t of 2. What is the meaning of this? What is the meaning of this? Can anyone please tell me? I mean, am I making myself understandable to you? Am I making myself understandable to you? This area, this subtracted area is nothing but this pt. Whether if it is less than pt, what is the next step we have to do? Again, we have to increase it to third one, W2 plus W3, yeah, plus W3 N3 bar. We have to do this. So we have to increase the K value. Yeah, for how many number of channels we are pouring water? Yeah, that's what. If it is greater than pt, let us say that, yeah, here, yeah, up to this we have filled the water. Yeah, filled water is more than pt. Filled water is more than pt. So what we have to do? Let us say that for n channels, yeah, we have poured water up to this. It is less than pt. It is coming less than pt. So how many number of channels we have to take? One channel only, right? Yeah, same thing they have taken. Here they are trying to calculate that K value for how many number of channels we can allocate the powers, so that remaining channels will be allocated with 0 power. Yeah, that's what they are checking. Whether it is less than pt or more than pt, yeah, based on that they are calculating K value. They are calculating number of channels, for how many number of channels we have to allocate powers. Once K is calculated, then obviously next step is PI values calculation, 1 by lambda calculation. What is 1 by lambda equation? Once K is calculated, sixth equation can be applied directly. Once K is known value, then 1 by lambda we can calculate. Once 1 by lambda we can calculate PI values in the fourth equation. So we are directly calculating with the smaller number of iterations, we are directly calculating the powers. Everyone understood? Are there any doubts here? With lesser number of iterations, we are trying to calculate the powers. That means for solving this water filling problem, we are taking smaller time. Yeah, next one. Yeah, let us say that now in water filling problem, we are having single constraint only, but here I have taken 2 constraints. Yeah, fourth equation is one constraint, fifth equation is another constraint. So how to solve this? Can you tell me? Any idea? I told you number of iterations we have to reduce. If we have to reduce the number of iterations, we try to go for closed form solutions, as many as possible. So it is like this. Yeah, just LKG problem. Here 2 constraints are there. Maybe it is related to the power constraint, maybe it is related to the interference constraint. If 2 constraints are there, how to solve this means, yeah, let us say 2x plus 3y less than or equal to 6. Yeah, let us say what to, yeah, what is that? Yeah, 1, 2, 3, 4. Yeah, 4x plus y less than or equal to, yeah, some 10. What are xy values here? How to solve for xy values? Remember, we have to optimize the capacity. At the same time, we have to follow these 4 and 5 equations. While allocating powers, we have to follow this 4th equation and 5th equation. Again, 6th equation also. But at the same time, solved powers or allocated powers should maximize the capacity. Top one, how to maximize the capacity? How to maximize the capacity here? Huh? Yeah, okay, you have your own method, but I am going for my own method, how I have solved this. So, equal to 6 I have taken, 4x plus y. Can you tell me what is the drawback of my solution? What is the drawback of my solution? I have taken simply equal to. But everything works fine if I take equal to. No, it can't be applied simultaneously. I mean, some problems will be coming. Always equal to, yeah, yesterday one madam asked, yeah, frequency selective fading, right? Yeah, I think it was madam. Here I have taken that channels are constant values. But once, by the time I do the resource allocation, what happens? Channel may change. Once coherent time is over, channel may change. Yeah, then I will be facing the trouble. Because I have solved this for only fixed channels. So I have taken this equal to here. So once I have taken equal to here, then x and y I can calculate for optimal capacity, for optimal data rate. Once I solve these equations by taking equal to x and y values, we can solve easily. Yeah, in that way, I mean, by using some, I tried to bring closed form solutions. Everyone knows what is the meaning of closed form solution, right? I tried to calculate the powers by using some equations. Directly by solving something, directly, I tried to allocate the powers without going for iterations. Yeah, here please see this, 8th and 9th equation. I tried to go for equal to's there. I tried to go for equal to's and I tried to solve. Again, please don't think that even solution for equal to also it is easy. No, here it is L are there. L additions are there. L additions means, please see, 2x plus 3y plus 4z something. Yeah, okay, what to say? Equal to, yeah, 6 value. Yeah, here 4x plus y plus something plus equal to 10. No. Is it easy to solve this? Again, you have to go for pseudo inverse or something. Pseudo inverse or something. It is not inversely solvable because 2, 3, 4, 1, yeah, something. This is multiplying with x, y, z equal to 6, 10. We can't calculate inverse directly. We have to go for some other methods. Yeah, I had to take care of this. That's why by thinking logical, I mean, by thinking something, I have come up with some solutions. Yeah, another problem is there. Another problem. For this, I want to inform you about heterogeneous networks. Heterogeneous networks. In heterogeneous networks means, please see the figure. Sorry, please see the figure. In heterogeneous networks means what is 5G or 6G? Main aim is to have seamless communication. What is the meaning of seamless communication? For example, yeah, until you are there in the border of NIT Warangal, you are using Wi-Fi of NIT Warangal. Yeah, let us say that you are moving on the bike or yeah, don't say bike, you are moving in the car. Yeah, as long as you move inside the NIT Warangal, you can watch the video in your cell phone by using Wi-Fi of NIT Warangal. But once you cross the NIT Warangal, once your car crosses the NIT Warangal, what happens? Wi-Fi of NIT Warangal won't work once you cross NIT Warangal. So what you have to do is, you have to connect with the 3G base station or 4G base station there. Because signal more power will be coming from 3G base station or 4G base station. Yeah, in that case what you have to do, but you should not stop watching the video. Even though you have crossed NIT Warangal, you should continuously see the video, watch the video in your cell phone while moving in the car only. Remember? So here, yeah, that is increasing the coverage area. One of the main aims of 6G or 5G is to improve the coverage area as much as possible by connecting multiple networks. Yeah, this first one is Wi-Fi access. This first one is, let us say, Wi-Fi of NIT Warangal, Wi-Fi network of NIT Warangal. The second one is 3G base station or 4G base station. Now I am moving in my car from Wi-Fi network of NIT Warangal to 3G base station, towards 3G base station. Then in that case, this NIT Warangal Wi-Fi network has to talk with the 3G base station so that my call or my video streaming will be handed over to 3G base station from the Wi-Fi network. Remember, I have to continuously see the videos in my cell phone. Even though I have gone to other wireless network, I have to get the video continuously in my cell phone. To get the video continuously in the cell phone, we have to do the handoff, right? Handoff. Remember, it is one wireless network, it is another wireless network. So doing handoff between two different wireless networks, is it easy or difficult? Is it easy or difficult? Remember, even for doing the handoff in between the same wireless networks base stations, it takes some milliseconds time. Yeah, for doing the handoff between one wireless network and the different wireless networks, obviously it takes more time, because I don't understand the language of you. Because I don't understand the language of you, yeah, it takes time for you to accommodate myself, to accommodate another user. Yeah, or it takes some time for my network to understand you, to understand your network. Yeah, something like that. Doing handoff between two different networks will be taking a long time. But do you want the handoff to be done, handoff to be taking more time? If handoff takes more time, what happens? Yeah, video will be cut off. Video streaming will be cut off in your cell phone. So that's why I will try to do the handoff within very possible time. And again, once it has gone to the other network region, after handoff is over, how much time resource allocation should be taking? Already handoff has taken some time. Handoff has taken some time. If for power allocation or for channel allocation also, if other network is taking more time, what happens? Already handoff time is over. For understanding between, for getting understanding between both of us, it is taking more time. Once I entered into your region, once I entered into your home, you have to do the facilities immediately to me. Yeah, otherwise, I'll be worried, I'll be scolding you. You are understanding, right? That's why here, as soon as it enters into some other network, the cell phone should be allocated with channels, the cell phone should be allocated with powers within very, very, very minute amount of time. So here also resource allocation should be taking very small amount of time. So that's what here. Yeah, please read this. I'm tired. I will sit by the time you read. You know about femtocells and macrocells, na? So if we are using, if we are allocating channel means, yeah, obviously that channel allocation will be creating interference to all the users. In LTE, if we are allocating channel, yeah, some F1 channel means that F1 channel allocation to me, to my cell phone will create, let us say that some smaller cells are there, so it will be creating interference to this small cell, this will be creating interference to, yeah, some other femtocell. So if I am allocating some channel, F1 channel to the user, because of this F1 channel allocation to the newly coming user, this will be creating interference to the femtocells. Around macro cell, so many femtocells will be there, so many smaller cells will be there. So this is the interference created to the first femtocell, this is the interference created to the second femtocell. Like that, I have taken V number of interferences. I have taken that V femtocells are there around the macro cell, around the major base station, so that V interferences are created. So here how many constraints are coming? How many constraints are coming? How many constraints are coming here? Yeah, this I1 is nothing but interference bearable by the first femtocell. I2 is nothing but interference bearable by the, interference tolerated by the second femtocell. Yeah, if I am creating more interference means even femtocells also will stop working. So I have to create interference. I have to create interference. Obviously it will be done, but that interference created to the xth femtocell should be smaller than the bearable interference only. Yeah, let us say that I can talk to you as long as you are traveling in the bus. Yeah, but for talking to you, after stepping down from the bus also, I can't barge into your home, right? Just like that. Even though I am not, okay, I have met some stranger in the bus. So with the stranger I am talking. With the stranger I am talking during my bus journey. But even after that stranger gets down from the bus and walked into his home, I can't just walk into his home to talk with him, right? I have to continue my travel. Same thing here. Yeah, that interference, the stranger can bear up to some amount. Whatever I have talked during the bus journey, yeah, obviously he has to hear. But even after stepping down from the bus also, I can't, what to say? I can't talk continuously with the stranger, right? Similarly to the interference also. Yeah, tolerable interference only I have to create for each and every femtocell. So here capital V amount of capital V femtocells are there. IV is the interference tolerable by the Vth femtocell. So this PM is nothing but powers allocated for my cell phone or something. Yeah, this is the maximization of capacity for the cell phone, and this is the interferences coming from the macro cell to the little cells, small cells or femtocells. So how to solve this problem? Any idea? How to calculate the powers easily here? How to calculate the powers easily? Remember I told you, as soon as I enter into the other network, I mean, I have to get video streaming. So that means for allocating the powers also it has to take very small time. So how to do this? Any idea?
Norma, we are having the far users and near users taking, and we are using superposition coding theorem. We can allocate the powers for the near users and far users. I think it's based on the superposition coding. We can allot the powers from the near base stations to far base stations.
Yeah, it is your idea, but I have solved this problem in a different way. Yeah, C equal to, we have to maximize the capacity. C equal to sigma Bi log 2 1 plus Pi Hi by sigma square. Yeah, sigma Pi less than or equal to Pt. Sigma, okay, what is there? Yeah, TMP. Tm1 Pi less than or equal to I1. Sigma Tm2 P2 less than or equal to I2. Something like this is there. So how to solve these equations? I mean, how I have done is, I have taken maximize the capacity equal to sigma Bi log 2 1 plus Pi Hi by sigma square in such a way that sigma Pi less than or equal to Pt, Pi greater than or equal to 0. This one I have taken it as one water filling problem. This is the first equation, this is second equation, third equation. This I have taken it as water filling problem. For this water filling problem, let us say that I am allocating powers for, yeah, let us say some 1, 5, 6 channels. Let us say that by solving the first water filling problem, I am getting power allocation for first channel, fifth channel and sixth channel. Again, I have taken the maximize the capacity with respect to Tm1 Pi less than or equal to I1. Pi greater than or equal to 0. This is second water filling problem. Second water filling problem. Yeah, this is the second water filling problem. Again, after solving this water filling problem, let us say that one channel, yeah, let us say sixth channel, some ninth channel. These are getting power allocation. Yeah, like that I solve all the water filling problems. After solving all the water filling problems, how to solve for the final thing? How to get the final thing? For which channels I have to allocate the powers? Yeah, let us say that two constraints only are there. Third constraint is not there. Two constraints only are there. For the first constraint, I got the channels power allocation as first channel, fifth channel and sixth channel. Yeah, by solving the second water filling problem, I got the channel allocation as first channel, sixth channel and ninth channel. I have done the power allocation. So, for which channels I have to do the power allocation if I am having 1 and 2 combinedly? Either you have to go for, so this is 156, this is 169. Either I have to go for union, or I have to go for intersection. Something I have to do with the existing channel. So instead of solving this, yeah, for solving this, yeah, it takes obviously so many constraints are there. It takes so much time for me to solve this. So instead of solving this, instead of taking long time to solve this, I am doing what, remember I have already solved water filling problem with a smaller number of iterations. So I will be taking very small time. I will be taking very small time here. If I take union or intersection, something like that. Yeah, I have done so many combinations, union, intersection, and okay. Yeah, I have done it long back. I don't know how I have done also. Yeah, I think I have taken union. Yeah, this proposition 2. Proposition 2. Okay. Any doubts here? I mean, again, I have gone for some other methods also. I am not discussing all those methods. You understood whatever I have told you until now? Okay, next is NOMA. Yeah, this is the work done by one of my PhD student, Srinu Sunkraboina. He passed out from here. So NOMA, non-orthogonal multiple axis. How many of you know about NOMA? How many of you know about NOMA? NOMA is 5G method. Yeah, you are NIT girls, no? Okay. Okay. What is the problem with OFDMA or orthogonal frequency division multiple axis? Yeah, orthogonal multiple axis. Second bullet. Orthogonal multiple axis means orthogonal frequency division multiple axis. Yeah, let me take it as, okay, 1 minute. What happened? Okay. Is it visible as it is? Yes, slideshow I tried to keep. Yeah, but I don't know why it is coming. Huh? Okay. OFDMA, what is done means we are having subcarriers. So this subcarrier, first subcarrier is allocated to first user, second subcarrier is allocated to some other user, third subcarrier is allocated to third user, fourth subcarrier is allocated to fourth user. Something like this is done in OFDMA or OMA. So here, but in NOMA what they do is, here they take same subcarrier is allocated to multiple number of users. Remember, in OFDMA, first subcarrier is allocated to first user, nth subcarrier is allocated to nth user. In that case, if you are allocating like this, what happens means you are not getting spectral efficiency. Here. So let us say that F1 is allocated to the first user, F2 is allocated to the second user. F3 is allocated to the third user. In OFDMA, orthogonal frequency division multiple axis. What is the spectrum efficiency? Spectrum efficiency means, yeah, let us say that the same example of T you take. Yeah, you went to the cafeteria. You went to some cafeteria to have tea or coffee. Yeah, because it is a owner's birthday. Because it is a owner's birthday, owner has given you freely cake or something. Cake or something. In that case, you are getting maximum benefit out of that owner. You are paying only 5 rupees to the owner, but instead of getting 5 rupee result, you are getting 10 rupee or 15 rupees result. Same thing. Here, if we are allocating a first channel to the first user, second channel to the second user, you are not getting efficiency, spectral efficiency. What is the meaning of spectral efficiency? How to the maximum extent we are able to utilize the spectrum. Remember, over the spectrum, even ministers also have done so many scams. Why means even 1 Hz spectrum also gives 1 crore rupees or something cost. 1 Hz spectrum also. Huh? Entandi?
It is very costly.
Okay. Thank you, ma'am. So that's why we want to utilize the spectrum to the maximum possible extent, because it is very costly affair. So what they try to do is, in a NOMA, they try to use the same spectrum. This is F1, yeah, user 1, user 2, yeah, some other spectrum is there, F2 spectrum, F2 spectrum, F2 spectrum. Here they are using, user 3 is using, user 4 is using, user 5 is using, same spectrum. Like that, same frequency channel is used by multiple users in NOMA. What is the advantage we get? What is the disadvantage we get? What is the advantage we get? What is the disadvantage we get? Okay. Yeah, okay. In OFDM, we are not able to utilize the spectrum efficiently, but whereas in NOMA, same spectrum we are utilizing for more number of users, so it increases the spectrum efficiency. So how they do is, yeah, please see this. Let us say that, yeah, this is F1 channel, this is F1 channel. So P1 power is allocated, P2 power is allocated. This is F2 channel, P3, P4, P5. So from the base station, same channel is utilized by, yeah, here UK minus 1, U2 signals. Yeah, that means that, yeah, here please see. Same channel is used by 2 users here. Same channel is used by other 2 users. Same channel is used by 2 users here. Why they are confining it to 2 users? Why not 3? Why not 4? Sridevi, don't respond. If we are using same channel by all the users, yeah, let us say we have allocated P1 power is allocated over the F1 channel to the user 1, P2 power is allocated for the user 2 over the same channel. So what happens if you are doing it like this? Tell me. What happens to the interference? What happens to the interference? If I am using the same channel for m number of users, what happens to the interference? Interference will be more, right? Yeah, that's why they try to reduce the interference and they try to limit the number of users to 2, maximum 3 or 4. In all the literature work, they did not, no other has used more than 3 users. So here what they try to do is, once power allocation is done, yeah, let us say that what they try to do is, yeah, P1 x1, P2 x2, yeah, PM, xm is the signal that is transmitted. Here x1 is nothing but signal to be sent to first user, xm is nothing but mth user signal. How they do is, base station will be sending P1 x1, P2 x2 plus PM xm. Here P1 is the power allocated for sending the signal to the first user, P2 is the power allocated for sending the signal to the second user, PM is nothing but power allocated by the base station for sending mth signal to the mth user. Here x1 is the signal to be received by the first user, x2 is the signal to be received by the second user, xm is the signal to be received by the mth user. So combinedly at a stretch base station will be sending. So here each user what they try to do is, they try to decode the other signals first. You know, everyone knows about successive interference cancellation, right? Yeah, sir told about V blast in the morning. What happens in the V blast? Successive interference cancellation. So first they try to decode. First, let us say that, yeah, it decodes, yeah, it decodes x1 signal. Yeah, let us say that this is mth user. This is mth user. First it decodes x1 signal. After that, after decoding x1 signal, P1 x1, yeah, P2, I mean H also will be there. H multiplying with P1 x1, P2 x2, PM xm. After decoding it, it tries to remove the x1 part. It tries to remove the x1 part. After removing x1, again it tries to remove. Now remaining is HP2 x2, HP3 PM xm. This is the remaining part. So again it tries to remove second signal, HP2 x2, HP2 x2, H means channel. So after that, in that way, HPM xm will be there finally. HPM xm means, yeah, its own signal. Mth user signal that it has to receive mth signal. That's why it is done. Successive interference cancellation is done at every user here in the NOMA. Yeah, same signal is sent to M users or K users here. Yeah, first it is decoding UK and it is removing UK part, and again it is removing K minus 1th part. Like that it is removing second part. Finally it is getting, first user is getting first signal. Again here also it is removing other signals first. After removing other signals only it will get its own part, its own signal. Again it gets its own signal by removing all the other signals. Everyone understood that this is the NOMA. This is NOMA. So how to pair this? Here students have taken pairing methods. Let us say that 16 users are there. 16 users are there. How to pair the users? How to pair the users? Remember, student has taken only two users per a channel. 2 users per a channel. How to pair them? How to pair them? They have taken it like this. I mean 1, 3 odd number of channels they have taken, and again I think 10, 12, 14, 16. Some even number of channels they have taken. I mean, has checked so many variations. Yeah, finally it has given better result, I think. How to pair the users is the topic now. So here, if ith user and jth user is there, from the base station to the ith user, HSI is the channel gain. From the base station to the jth user, HSJ is the channel gain. So in that case, he has divided the power allocations into PI power allocation is done according to the channel gains. Alpha means, you know, right, path loss exponent. Path loss exponent depends on line of sight or number of obstructions. So here he has divided the powers into total power to be allocated over the channel, F1 channel or F2 channel, total power PS multiplying with, he has divided the power allocation as per the channel gains. HSI is the channel gain from base station to the ith user, HSJ is the channel gain from base station to the jth user. How much time is there? You want me to stop here or? Yeah, I thought you say okay. Okay. Here, so based on the channel gains, he has split the powers. So that means that PSI is the power allocated for the ith user, PSJ is the power allocated for the jth user. Here, tell me the equation for PSJ. Tell me the equation for PSJ, power allocated for the jth user. Power allocated for the jth user. Yeah, out of PS power, this sixth equation power is allocated to the ith user. Out of PS power, how much power we have to allocate to the jth user? That's what I am asking. Yeah, minus means what is that? Yeah, PS multiplying with HSJ whole square divided by total sum will be the power allocated for the jth user. According to the channel gains, the student has done the power allocation for a particular user. Yeah, how to pair the users? I will show the MATLAB code. Yeah, here. Total power they have taken it as, total power that is there for two users is 30 dBm. 30 dBm. So 30 dBm is converted into, yeah, linear scale in terms of watts or milliwatts. In terms of watts or milliwatts. So B is the bandwidth allocated for each channel. B is the bandwidth allocated for each channel. Yeah, if you don't understand, please ask. I am rushing through. Yeah, this is the noise power. This is the noise power. What is the noise power? What is the thermal noise power? KTB. Thermal noise power KTB. K Boltzmann constant. T is temperature or something. B is bandwidth. So that KT value is minus 174 in terms of dBm, I think. Yeah, this is a KTB. That KTB in terms of dBs. He has calculated. Yeah, same noise when converted into the linear values in terms of watts or milliwatts. Yeah, this is the noise power. This is the noise power. Again, eta equal to 4 is, yeah, path loss exponent. Path loss exponent is taken. Here number of users, he is taking it as a 4:4:40 means, I don't know why he has taken it like this. I got the code yesterday only because I have to teach you today. Okay. Why? Yeah, okay, it is not going. So K equal to 4:4:40 means 8, number of users, he has taken it as 40. Out of 40 users, he is splitting into 10 users group. First 10 users one group, second 10 users another group, third 10 users another group. Something like this is splitting, I think. Yeah, over 10 channels he has taken. Over 10 channels he is doing that NOMA. Here MC means maximum iterations he can have is taken as 3 into 10 to the power of 5. Once the number of iterations goes beyond 3 multiplying with 10 to the power of 5, he is stopping the work. So number of iterations, first iteration is starting here. First iteration is starting because it is for loop, iteration equal to 1. In the one iteration, yeah, if it is running, it would have been better. Okay. Okay. First u equal to 1 is taken in the first iteration, s equal to ku by 2. S equal to ku by 2. That means that, maybe, I am thinking, it is my thinking only. Yeah, he is splitting into top parts and bottom parts, I think. First one, red and green ones. By 2 he is doing means maybe he is splitting into user pairs. I don't know why he has taken again the noise here. Here, really I did not understand this. How he is calculating the channel gains here? Yeah, what I understood here is, after reading his code, yeah, this is some Gaussian he is creating. Gaussian, yeah, random means normal distribution. He is creating a normal distribution for n channels. Again, another Gaussian distribution for n channels. Another Gaussian distribution for n channels, imaginary part. So this is nothing but a complex Gaussian distribution. So again, h should be equal to square root of capital H square, real part of h square plus imaginary part of h square. That's what we have to take to calculate the Rayleigh fading. To calculate the Rayleigh fading, we have to take root of real part of h square plus imaginary part of h square we have to take. Yeah, I did not understand this function. In the similar lines only he has taken. This is finally channel gains of Rayleigh fading for all n channels. For all n channels or n users, I think. N users or n channels? N users. N users it must be. So here these are G is nothing but Rayleigh fading channel gains for n users. Again, he is arranging the channels into descending order. Yeah, these channels are arranged into descending order because he has to pair now. Yeah, let us say that I have paired with 2 good channels. I have paired 2 users with the good channels. Let us say fighting is there. Fighting is, what is that? Wrestling is there. Wrestling competition is there. If both the wrestlers are, this much, what happens? If both the channels are this much, fat, what happens? First wrestler will fight with the second wrestler will get injuries, first wrestler also will get injuries. That's okay. That's okay because both are strong, no problem at all. But if you are having wrestling competition between lean person and fat person, what happens? Yeah, lean person obviously will get more injuries, right? So how much power we have to allocate? Before coming to the regular competition, what should the lean person do? Before coming to the wrestling competition, what should the lean person do? He has to use drugs or he has to eat some banana or something. He has to drink glucose or something before coming to the wrestling competition. So that's what we are doing is, For the weak channel, we are trying to allocate more powers. For the better channel, we try to allocate lesser power. Something like that they are trying to do here. Yeah, that's why they are arranging the channel gains in descending order or increasing order. To choose the pairs, yeah, with equal fairness. Yeah, he is arranging he is arranging the channels in descending order. He is arranging the channels in descending order. Yeah, this and all he has taken another methods for comparison. Whatever he has done, I will explain that only. Okay. Tell me, for I equal to 1, yeah, let us say that for I equal to 1, for I equal to 1, channel gain as it is taken, channel gain as it is taken. For same channel gain, for the first user, if I equal to 1 is there means, he is pairing with what is the ku bar minus s minus I, yeah, something. Yeah, he is pairing pair 1, please see, user 1 is paired with user 10 here. User 1 is paired with user 10. Similarly, on the same lines, if he is taking ith user is paired with, yeah, k of u minus s plus I. This user, ith user is paired with k of u minus s plus ith user. That's what is my understanding from his code. So after pairing them, I think he has checked so many combinations here, as per my understanding goes. Yeah, this is what he has done. Yeah, this one. Please try to understand. What is the meaning of this? For ith user, A to P is nothing but ith user power allocation. Ith user power allocation, what is the part of ith user power allocation? Yeah, please check channel gain whole to the power of alpha divided by, yeah, combination of channel gain whole to the power of alphas. Same thing he has taken here. How much part of total power is to be allocated to the, yeah, some A to P user. Yeah, channel gain must be GSP has taken some variable, channel gain whole to the power of minus alpha, divided by combination of channel gain whole to the power of minus alphas. Yeah, this will be coming as, yeah, some 0.4 is coming here, Out of total 1 watt, 0.4 watts is allocated for one user out of the user pair. Remaining thing, 1 minus 0.4, that means 0.6th part, 60% power is allocated for paired user. You are able to understand what I am saying, right? How much powers that guy is splitting the powers as per the channel gains. So out of PS equal to 1 watt, how much percentage is to be allocated with for the first user, how much percentage is to be allocated with paired user. That's what he is trying to calculate. So some 40% is allocated to the first user, means to the paired user 60% will be allocated. Yeah, again he is calculating. After that PSK multiplying with, yeah, here Yeah, try to understand. This is nothing but B is a bandwidth. B by S means maybe S number of users are there. S means 2 I think here. S means 2 users are paired. B by S means available bandwidth. Yeah, same bandwidth is allocated to both the users. So here PSK is the total power available 1 watt. Out of that, alpha part is to be allocated to the first user. GWP means, yeah, maybe channel gains. Channel gains. Yeah, please see. Yeah, why it is there here itself. Yeah, please see. Data rate available to the ST user, data rate available to the kth user is nothing but B log to 1 plus PKS. PKS is nothing but how much of power allocated to the user. HKS is the, yeah, power, channel gain for the kth user or something. This equation, same equation is solved by him to tell that this much capacity is available for the user after power splitting. You are able to understand what I am saying, right? If you are not getting anything, please ask. If 1 watt power is there, out of 1 watt, please check. Pair 1 is nothing but user 1 and user 10. User 1, for a user 1, if 60% power is allocated, yeah, for a user 10, yeah, for remaining 40% power is allocated. And power allocation depends on the channel gains as per his paper. After allocating the power, channel gains means it is based on distance only, na? I mean, his concept is different. According to his concept, I am explaining. So after allocating the powers, he is calculating the data rate available to the user 1, data rate available to the paired user. Yeah, that equations are given. Yeah, this is nothing but, these are nothing but splitting powers for the user pair. These are nothing but capacity coming for the ith user and other paired user. Everyone understood this, right? Yeah, 517. Actually, I wanted to explain UAVs also. Can you listen? I wanted to explain about UAVs also. Yeah, I will try to explain it in brief. Okay. Okay. Huh? These are available in net, na? Yeah, you please download it because it will be benefit to me. Code, no, code is not available. Yeah, I will send the code, no problem, because it is already published, na? Okay, na? Yeah, then please carry on. Spectral efficiency, sir. Because in orthogonal frequency division multiplexing, even though we are having orthogonal subcarriers, we are not able to utilize all those subcarriers fully. Yeah, but in NOMA means, even though same carrier is there, that carrier will be utilized by more than 2 users. More than 2 users or at least 2 users. So spectral efficiency will be more. But the problem with NOMA is successive interference cancellation. Because successive interference cancellation is involved means, yeah, we can't have NOMA implementation for more than 3 users or 4 users for one frequency channel, because it becomes a long time. Yeah, I mean, he has explained it. Yeah, read this, sir. Large decoding delay means, if you are using the same channel for 100 users means, yeah, by the time each user gets the signal, 100th iterations are to be done. V blast receiver in the morning. Yeah, serious error propagation. If by any chance he is using one channel, base station is using one channel gain, you have to calculate this powers and all. Yeah, by any chance base station did not predict the channel gain properly, or receiver did not predict the channel gain properly. So what happens if if the user did not predict the channel gain properly, because based on the channel gains only we are doing decoding, successive interference cancellation. If one signal goes wrong, yeah, we are subtracting that decoded signal, the decoded signal itself goes wrong. Yes, again obviously second decoded signal also goes wrong, third decoded signal also goes wrong, 100th decoded signal also goes wrong. That is the problem with the successive interference cancellation. Everything goes wrong. If one thing is going wrong, everything goes wrong. Okay, na? Okay.